A one, a two, a 1, 2, 3, 4. Does that work? Did that scare anyone? I give you a count up, at least. Let's see. Does anyone actually hear me now? And how many people got scared this time? Yes. Okay, cool. I managed to scare people again. Yes. Hear yes, see no is the correct state of affairs. For now. Let's see. Now I gotta do this. And where's my... Slowly but surely we're getting there. Devices. All right. My light was wrong, but now my light is correct, but also very sharp. All right, let's see if you can see me. Like so. In theory, you can now also see my face. But this light is very bright on me, but I think it might actually look correctly to you. Or is it too sharp and bright? I made some changes to my settings, and now I gotta make sure the settings are actually correct. The volume is low. Alright, let's see if I can do something about that. I can certainly move this closer to my face, but then I can also do properties. No. Advanced audio properties is what I want. And then over here, it should be about right. Like, looking at my volume meter, at least, my output volume is correct. But maybe your input volume is down? You're crystal clear, but maybe too bright. Okay. Yeah, I know. I need a soft light on the other side. It is one of my current problems with my setup is I don't have anything over on that side. Let's try this, shall we? That seems slightly less wild. And we'll even do this. Okay, that should be slightly better. So now I should be less overexposed, and volume should be roughly right, which is all we need. Much warmer. I mean, I did not make it warmer. I just made it less bright. But I think that's yeah, this time at least we're not stuck in the OBS settings. Now it's just the physical things. Cool. All right, we have roughly the right lighting. We have roughly the right sound, which I think means we're just about ready to go. Yeah, I swap back and forth between these glasses and these glasses. And anytime I wear these ones, people go, "Oh, you're wearing glasses." And when I wear these ones, they don't even register. So I figured, why not do a stream with these this time? I should be a full-time streamer. I mean, someone's gotta pay me to make that work. But I mean, maybe. I would play a bunch of like programming games too. It's funny, after the one stream I did where I did like assembly level ish, or not assembly level, embedded device ish programming game. I got a bunch of emails from other creators on Steam who were like, "Hey, try our game too, please. We also have programming in it." So I could probably do that just sort of separately. Okay. Yeah, they are orange, partially because I really like the color orange, and partially because Rust. It's the same thing with my drawing tablet, which you can see here, is also very orange. I don't know. There's just something about that color. It's since before I even adopted Rust, I started doing that. Okay, I think we should maybe get started. Let's go ahead and see if I do this. If I haven't completely broken my setup, you should now see my screen and my face up in the corner here somewhere. It's hard to point here when I'm already in that corner, but you know what I mean. I do not have an orange iPhone. I have a like a lime green Android. It's a Pixel. Excellent. All right, then I think we're just about ready to start. Let me get this all set up. Where's my water? Here's my water, so I don't die. I also have. I'll show you. This is for comparison. This is a normal webcam. This is like a Logitech something stream cam. So the difference in quality between that and this is fairly big. All right, anyway, back to screen. We'll actually do the thing. Can you move it to lower right bottom? No, because that tends to overlap more with my terminal command line. And so I'm going to keep it top right. All right, I think we should start. So how about we start recording and kick it off? Hi folks, welcome back to yet another Rust stream. This is going to be an impl Rust where we sit down for several hours and just hack out a bunch of Rust code that does something hopefully interesting. There's just tiny bit of housekeeping before we start. Number one, this channel just hit 100,000 subscribers, which is really, really cool. It means YouTube sends me a plaque. So eventually I will have a plaque, which is fun. It doesn't really mean anything beyond that, except I guess yay us, we did it. We made a big YouTube channel of people who care about writing Rust code. So that's really fun. Thank you for those who subscribe who make that be the reality. It's fun. We now have a big number next to a Rust channel. The other thing is I've created a discount code for Rust for Stations on the No Starch website. So it's YT100K, YouTube 100,000, which gives you, I think, 30% off the book or 25% off the book. I don't remember, but go check it out. So that might not be active anymore by the time you look at this afterwards, depending on how late you are to the videos. But for those who are watching live and for those who watch it shortly after it being published, you'll be able to use that code to get a discount on the book to celebrate. And related to this, just a reminder that I do also have a GitHub sponsors active. So if you like these streams and want me to do more of them, you can go sponsor there. And then, hopefully that gives me room to do more of these. And maybe other kinds of streams too. Who knows? Cool. I think it's time we dive into the thing we're going to do today. It's been a little while since we did an impl Rust. And partially that's because I wanted to find the right topic, right? Like the right thing for us to spend 7 hours coding on. And then I came across this thing called the 1 billion row challenge. This is something that was posted in the Java community back in early 2024. And it was basically, here's a billion row, essentially CSV file of weather data. So it's basically city and temperature. And your goal is to produce a program that outputs the minimum, maximum, and mean temperature for every location, so for every weather station, in the data set, and do so as quickly as you can. It was published for Java, so specifically like all the infrastructure around it and all the testing and all the results that were published were all in Java. And if you look at like the official repo for this, I'll put the link in the video description. You'll see down here that there's sort of a ranking of the results for how quickly different people did it. And they did it using there were a couple of rules for how you needed to do it in Java and what you could and couldn't do, and which VMs you could use and everything. But ultimately there's like a results that were computed by the person who set up this challenge. And it was set up to be evaluated on a very specific kind of cloud instance. And you got this many cores and like everyone got the same input file, but it was randomized. And then there's also results for what if you give it more cores, or what if you give it more kinds of locations in the billion rows. Like more distinct keys and so on. But ultimately, like, this challenge ran for a while, and then it's done now. Like, there's no more additions being added, at least as far as I'm aware. But obviously what happened is that people got excited about this and started wanting to do it in other languages. So over the course of 2024, you'll see here there's sort of a discussions page, and in the discussions page, there's people doing it in lots of other languages. And you'll see here, if you look at the right on the comments, you'll see one of them has 61 comments in the thread, and lo and behold, it's Rust. So this apparently got people excited in the Rust community too, partially because people like these kind of challenges, and partially because I think Rust people just like writing performant code and see how much they can push out of it. And so there's lots of cool solutions in there. There was sort of lots of iteration in the ecosystem, and people trying to find, like, how can I really extract every last, microsecond of time from this? I was not aware of any of this. I found the 1 billion row challenge, I don't know, like, I guess I found it maybe a year ago, and then I just put it in like a log somewhere of maybe I'll do this one day. And then I was looking around for stream topic, and I was like, wait, this is a great topic. How about we just do this? And one of the reasons I wanted to focus on it was because the challenge itself is really simple. And in fact, where we're going to start today is just to write like the stupid naive implementation that just does this and just see how long it takes. Like, I think with the Java version, there's included like a obviously correct but slow version, just to give people something they can compare the results from. And that one takes, I think, about 2 or 3 minutes to run. It's like single threaded, like super straightforward code. And we'll write that in Rust 2 and see how fast that is. And then we'll iterate on profiling why it's slow, figuring out what we can do instead to make it faster, and see how much we can get that down. In the actual challenge, the winner with when run with the 8 cores on the particular instance that's being used runs in 1.5 seconds. Now, I also checked these out locally just to see, and the winner here, so I took the winning solution that won in the most categories, so not just the one that was fastest on that particular instance, but that was like the highest ranked in both 8 cores, all the cores, and the more distinct keys, just to have avoid sort of comparing to a hyper optimized solution to that particular problem set. And you'll see that this, like, one of the problems that you'll have is that Java has to compile it and stuff, but if I run it again, this completes in basically no time, 800 milliseconds. And that's because it gets to use all the cores on my computer and everything, so it'd be faster than the 1.5. But this is, you'll see at the top here, this is not even the fastest version of this solution, because I'm using it in the standard JVM, not the Graal VM, because I don't have that installed and I don't want to install all the Java infrastructure for managing SDKs and JVMs and everything. But like, clearly it's possible to make this very fast. I don't know how close we'll get to this, but we'll profile our way there and see what we get to. Cool. Let's go here, cargo new. Now we got to pick a name. Now, a name for this, we could just call it Billion Row Challenge, but that's no fun. What can we do instead? Let's do... 1 billion rows challenge. So the logo for the official repo is the emoji for 1, the emoji for B, and then the emoji for a race car, because RC, row challenge. So we could do something stupid like beeswax, because it's trying to wax things so that they can be fast, but it's B for billion. Formula 1. Wet thrust is not good. Don't like that at all. Brr. I like brr a lot. I like brr a lot. It goes brr. Okay, brr it is. That's great. Okay, now we're also going to pretty strictly follow the rules of the challenge. So I skimmed through like the Rust thread discussion, and I saw that there are a bunch of solutions that like don't actually follow these rules, and I want us to actually follow these rules. So obviously the use these versions of Java doesn't apply to us. But the other things we want to follow: no external library dependencies may be used. Nothing outside of the standard library. Implementations must be provided as a single source file. I'm not too concerned about that one. Computation must happen as application runtime, so you can't like do a build RS that does all the compute as your program completes in like constant time. For input values, so the format here, we'll look at the exact file, but it's like station names, and then I think it's a comma, and then the temperature, and then a new line, and then lots and lots of these. The station name is non-null UTF-8 string of a minimum length of 10 characters and a maximum length of 10 bytes. But notice that this is a UTF-8 string. It does not contain semicolon or new line. I guess semicolon is the delimiter. And there's no guarantee about which UTF-8 characters are in there. Like there's no guarantee that they're all like ASCII compatible or something. So we need to make sure we actually handle arbitrary Unicode names. And the temperature values are non-null doubles between minus 99.9 and 99.9, always with one fractional digit. So we want to make sure we actually conform to those rules. Maximum of 10,000 unique station names. Line endings are new lines on all platforms. We're not allowed to rely on specifics of a given data set, so we can't hard code the list of stations or anything. And the rounding of output values must be done using the semantics of IEEE 754 rounding direction, round towards positive. Okay, so those are the rules we need to follow. No libraries, but stdlib is okay is very unfair between languages. Totally true. Part of where I'm coming from here is like, I think in Rust this is doable without external dependencies, and so I would like to just follow that rule. It's true that like for some languages that would just be unreasonable, but for us that's what we're gonna go by. Okay, but well, let's see what we get to. So here's a input file I prepared earlier. Others, one BRC. And it's called measurements.txt. So if we ask for the number of lines, you'll see it's 1 billion lines long. And if I asked for the first couple of lines, this is what it looks like. So it's just semicolon delimited columns, new line separated rows. Now, this is easy, right? Like if we were to just do this with like standard Rust, like nothing fancy in here, you know, we'll do let mute f is file open. Measurements.txt, and this is an unwrap kind of program, and then I will bring in file, and then I'll probably do like a in fact I'm not even going to use I need a buff writer so that I can do by lines, so I will do buff reader new of f, so that means I don't need mute here, and then I will do for line in f dot lines, and we'll do something like a hash map here, and in fact we can do with capacity 10,000. We know there are never more than 10,000 stations, so let's actually, no, this is an optimization. We're not doing any optimizations in this round. And for every line, we're going to do line dot line is line dot unwrap. Wait, why is it unhappy about this? Oh, right, because I need to bring in buff read. Line here as a result because reading from the file might error. And then we're going to do station and temperature is line dot split ones by semicolon. Again, dot unwrap. We will do... We're going to not do any optimization. Okay, I'm so tempted to do optimizations already, but I'm going to try to resist it. Temperature is going to be temperature.parse, and we'll do this as f64.unwrap. And then we're going to do stats, and we're going to do stats.entry station to string, and then or default. So this is going to be stats is this. So stats now, right, it doesn't know the type here. What I'm going to say the type is 3 F64s, the min, the mean, and the max. So stats here is going to be a mutable reference to one of those. And then we'll do stats.0 is stats.0.min with temperature 1, 2, max. And actually, this is going to have to be, I think to keep a running mean, we actually have to do this. And I know this could be a struct technically, but we're going to plus equal temperature and do plus equal 1 for the count. We need or default here so that we insert the station if it's not already in there. And then after we're done with all the lines, then I think we have to print the stations in like in alphabetical order. Let me see if that's true. So what does this print? Yeah, these are printed in alphabetical order in this kind of hash map syntax. So that means we're actually going to make this a B tree map. Again, we're not optimizing. We're not optimizing yet. And then we're going to do for stations min sum count max in stats. Right, and this is actually going to be a string key. And for each one, we're going to do print of an open curly bracket. We're going to do print of, what's the syntax here? It's just like station equals min slash something slash max. This is then going to be sum divided by count. And then this actually needs to be, we need to make sure we match this sort of comma separated syntax. We're going to do, we're actually going to say stats is stats.intoIter.peekable so that we can check whether it's the last one. Again, no optimizations. We're not allowed. While let some, so we'll do a manual iterator here. Is stats.next. And then if stats.peek is sum, then we will print a comma space, and then we will print end of curly brackets. We need the double so that it doesn't think it's a format specifier. We're not doing any optimizations. We're not doing any optimizations here. There's no like and modify. We're not doing any like sort after the fact. All of those are optimizations. We're doing the stupid thing. And I guess we should put the others measurements in here. So build with release. Oh, Why is it unhappy with me? Because this needs to be this. And can't divide this by this. That's because this has to be ASF64. Actually, wasn't there recently a idiv or something? I feel like they added a... No, it's the other way around. Okay. This has to be mutable because it's an iterator. And now it should be happy with us. This doesn't need to be this anymore. All right. So what happens if I now do time this? So again, this is single threaded, right? So if I do htop, so using 100% of one core, which is what we would expect to happen. Let's cd into bur here as well. And it's just going to run as fast as it can. Your min-max is thrown off by the default 0 on arbitrary data. Oh, you're right. You're right. This would be wrong. So we actually do need to change that. But even so, like, that wouldn't really affect the runtime here. It's still going. Now, I think when I ran the default Java version, it took me about 3 minutes. So we'll see if this is equivalent. Buff read is a memory optimization. So yes, but the reason I used buff reader here, and I think that doesn't count as auto optimization, is because it gives me dot lines, which is like a very idiomatic way to be able to iterate over the lines of a file. The min should start at F64 max. Yeah, you're right. What is time? Would you put before cargo R? So time prints the total time it took to execute the command. Sort of a shell built in. I guess we could fix this while we're at it, right? So this would be or insert. This has to be F64 max. This can be 0. This is 0. And this is F64 min. Right, technically. Okay, so it ran this. It took 98 seconds to run. It seems to have printed something kind of reasonable. Let's see if we compare it here. So Izmir, for example, should be minus 37.1. Minus 37.1. 17.9. We got 17.89 and so on. And 67.1. 67.1. Okay, so this seems like just from a random sampling with an n of 1, this seems right. We'll add this in. We also need to make this print only to 1 decimal place. And actually the same with these, but it shouldn't matter because these are always values that are taken out of the input, and the input always has precision of length 1. But even so, we'll retain that. Oops. Cool. Okay, so now we have a comparison point. About 100 seconds. This is already faster than the stupid Java version, but they're not really comparable, right? Because we get to compile and like we don't have a runtime and everything. But this is still like very slow. Okay, so let's go ahead here and git add. I'm going to git ignore measurements.text because anything else would be insane. Then we're going to git add these. Stupid version. Now let's start to do some optimizations. We'll do the simple optimizations first, right? So simple optimizations here include things like so the B-tree map is a little sad. We could have a hash map instead, which is usually faster to access, and then just sort the keys at the end. That might give us a slight speed up. The lines here is not terrible, right? Like the lines here is You read stuff from the file into a buffer in memory. You search for the new lines in memory, and then you yield the subslices accordingly. So that one's not too bad. The split ones here just searches for the first semicolon and then gives you the stir slices on either side. This is probably pretty costly because it means that we're allocating a new string and copying them for every station, even though most of them will already be in the map, so we didn't need to do the allocation. Minimax here shouldn't be too bad. And this only happens once at the end, so I'm not too costly with it. Okay. So there's some sort of interesting things here, but what I really want us to do is have a look at perf record of cargo run release and see what we get. Because it is otherwise... What? Oh, graph is maybe the default now? Because it can be tempting to sort of guess at where the slowness is. Report-g. Let's see what we get. Right. Okay, so we get basically nothing useful out of perf. There are a couple of reasons for this, but the main one is we're compiling in release mode. And so in release mode, you don't get any debug symbols. Okay, that seems like a problem. Let's go ahead and fix that. So we're going to say profile.release. We're going to say LTO equals full, even though that probably doesn't matter here. So this is like linking optimization so that you get better inlining across stud and rcrate, for example. We're going to say panic equal to abort so that we get rid of all the panic machinery. That doesn't matter to us. We'll also say debug equals true. And just to see how that affected things. Oh, right. It has to be thin or fat. All right. Fat. I just wanted to see what the impact of these are to begin with. It might be basically nothing, but just so that we've done the things that people are going to later be like, oh, you obviously need to do this. There's another one, which is like codegen units equals 1, I think is decently common. I don't think that would matter a whole lot here because the program is very small. It's not clear to me we would end up using lots of codegen units in the first place anyway. But let's see. So the previous time was 98 seconds. And we have also enabled debug symbols, which I think on Linux, they forget whether they split the debug info. So that might end up making the binary bigger. And if the debugs, but the debug symbols shouldn't really affect the performance all that much. But I think we're about to find out. Your cargo colors are weirdly colored. They are gray instead of green. I don't know what to tell you. They turned gray a few months ago, maybe? I'm not sure why. Maybe it's my color scheme that's sets something wrong somewhere. Oh yeah, target CPU equals native. That's another good one we should set. Okay, this ran in 90 seconds. So it did do something. Let's do target CPU equals native as well. Oh, what's the... Do I have to set that through Rust flags? I think I do. Isn't there a way to set it directly here? Can I do this? Oh, right. Oh, it's not stabilized. Do I really have to do it through cargo target CPU native? Yeah, I think I can set it, instead of setting it here, I can set it in cargo config.toml. I can set, I forget what the, aha. Yeah, I guess. It makes me sad, but all right. It's like also a little unclear how much this will help us because the standard library comes pre-compiled. And so I'm not sure we're going to get the optimizations we want here for the standard library part of the code. But let's see. Okay, so we're comparing to 90 seconds. And now this will be with target CPU equals native. Let's see how much of a difference that makes. For those who aren't familiar with this, like target CPU is normally when Rust tries to build binaries, it tries to build them for a sort of generalized version of your CPU, right? So for if you're on x86-64, for example, it'll build a binary that's runnable on like most modern x86-64 CPUs. But there might be like my CPU specifically supports some newer instruction sets than the sort of the lagging behind general purpose target of x86-64. So it might have some optimized instructions that if we make use of will make the program faster, but also if we make use of them, then the program will not run on other people's computers. And so it sort of depends on whether your goal is to make binary artifacts that are going to run on other computers, like if you're shipping a distribution. In my case, I'm not doing that. I'm just running it locally. So I'm fine with Rust being able to take advantage of those extra assembly instructions or extra operations that my CPU specifically supports. And so that's what target CPU equals native will do. 92. Okay, great. So it's slower. Perfect. That's fine. We'll still leave that in there. Nightly features I think are okay. So portable SIMD I think is the way we're going to get SIMD. And we could do build stud. I guess let's do all right, set nightly just to get that out of the way. And then sure, why not do build std? Oh no, it's not. It's -z build std. So now it's going to build the whole standard library also from source. This is a nightly cargo feature. Oh, it's unhappy about that, huh? Cargo target. I believe you. Let's see. Yeah, so with target CPU equals native, it should make use of all of like the MMX and SSE and AVX standards that my CPU supports. Why? This is one of the many reasons why build-std is not standardized yet. It is unhappy. Yeah. I wonder why it is unhappy about this. All right. We might just ignore that for now. I don't think rebuilding std here is really going to make like a huge difference to us. So we'll stick with our good old without build std, and we can always do that later. Time will include the build time. But as you can see, the build time here is basically nothing. But it's true. I mean, I'm happy. I usually would run either cargo build release first, or I just cut it after I see it start running and then start running it again. Yeah, I'm guessing this is still going to be about 90 seconds. We haven't really changed anything interesting. Okay, so now if we do, I'll add in .cargo and add cargo toml. And then we will do perf record -g cargo run release. So now we're just going to do a perf record, which is going to record a bunch of performance statistics about our code and figure out where is it spending its time. And so we'll let that run for a little bit, and then we'll do perf report -g to see where time is now spent. A bunch of time in libc. Oh, why? What? Why is it not giving me libc symbols? Oh, that's because headers? No, libc, I forget what they're called on Arch. I thought I already had these installed. But what's it called on Arch? What? What? Oh, it's because I need to it's pacman conf. I need to include is it core testing? No, it's not. Arch dlibc headers. There's like an alternative thing you can do to get the dlibc headers. Why can't I find it? There's like a separate repo you need to enable. Yeah, they're dev. No, it's not. It's not. They live in a separate repo, but where? Why can't I find it? This is annoying. I should have looked this up in advance. Sorry about that. No. No. Let's see if Google is better incognito than this. I don't think it's Linux headers, because I think I already have Linux headers. Yeah. I'm confused. I was pretty sure I already had these. Libc dev? It's not usually called that on Arch. Incremental equals false shouldn't matter for the release build here. Is it because I need to actually do this probably? No, that's the Linux headers. I'm very confused because I'm pretty sure I've done this before. Yeah, you see the debug symbols on your Arch setup. I think it's just something I don't have installed. Oh, unless it's help record. Yeah, it's because I need call graph dwarf, I think. Let's see if that helps. There we go. See how much more data it wrote. Cool. Yeah, that's fine. All right, now we're talking. Okay, so you'll now see that there is our main, and if we go into main, oh, no, that's not what I want. No, that's also not what I want. And you'll see here, like, if you haven't looked at the output of perf report before, it shows you self, which is the cost of this function, excluding its children. And children is the percent of execution time that went to this function and its children, right? So if function A calls function B, then the cost, the self cost of A is the time it took to execute A minus the time it cost to execute B, and children is the time it took to execute A, including the time it took to execute B. And so you'll see there's a bunch of various key things you can do here. In particular, plus lets you expand down into it. So if we go into main here, you'll see that a lot of the time here is spent on the entry into the B-tree map, which is in turn spent here on going into the B-tree and specifically the compare operation for the B-tree map, which isn't terribly surprising, right? Like most of what we're doing with every entry is doing a lookup into this map. We're spending a little bit of time on the parsing, a little like 4% of time on our allocation and deallocation of strings, right? So this is the allocation and this is the deallocation. So we're spending almost 10% of our program just allocating and deallocating strings. So how about we try to do both of these at once? So we're gonna go here. We're going to switch this into a hash map. Then we're going to here match on entry instead. We're going to match on, we're actually going to match on get. We're going to match on get mute. And if we get a stats back, then we'll get stats. If we get none, then we will do this. We'll do stats dot insert station to string of this. And in fact, we can do yeah. So the thinking here being we're going to do a lookup without allocating a string. And this is going to use hashing and lookups rather than using the actual comparison of the string key. And then we will do, if it's there, then we just return that entry. If it's not, then we will insert the entry. Is there a get? No, there's not. Okay, so I think the easiest way to just get a mutable reference out of this is to do or insert this. Like so. At least, yeah, because insert returns an option of the old value, whereas what we want here is a mutable reference into the stats. So that's one. That gets rid of the string allocation. We've changed this to a hash map. And now here we can, there are a couple of ways we could do this. We could either sort all of the keys or we could just move them into a B-tree map. They end up being roughly equivalent, I think, but we can do a, keys is stat.keys.collect. Then we'll do keys.sort, and we can do sort unstable is fine. Then we will do keys is this. Actually, this will be a little slower because we need to do a... so what we'll get out of this, right, is just the keys. And then for each key, we will need to do a lookup in the map. I actually think if we here do a B-tree map from iter stats, and then just keep this the way it was, then we save all the lookups. Right? Because we don't need to do a lookup in the B-tree map. We don't need to look up in the hash map. We just do the construction once. And this doesn't need to be... Okay. So let's do cargo B release. So remember, what we're comparing to here is about 90 seconds. Why not a vector of tuples and then sort by key unstable? Oh, I see. Just turn the hash map into a vector that includes the keys and the values. That's not bad. Let's try that. I just want to see how much. So we optimized out the the string allocation, the string deallocation. We moved away from using string equality to just using the hashing. So this should be based on our perf at least 10% faster. So it was 90%. We should cut about 10% of the runtime. So it should be around, it should be no more than 80 seconds. And it's 52. Okay, cool. So git diff. This one is now fewer allocations and no partial comp. Okay. Let's try the proposal here, which was stats into iter collect stats. So I think this will basically not matter. And the reason for that is, right. The reason for that is this is the printing at the end. Why? Oh, right. By a b a dot 0 compare b dot 0. Yeah, so I don't think this would be a lot faster. And the reason for that is because it's really just the printing, and the printing is printing very few records. Sort by key versus sort by, they end up being about the same. There's no huge difference between them. In fact, I think sort by is supposed to be faster than sort by key. I believe I read that at some point. Maybe it's actually in the standard library documentation. But this is an example of something where if we do a profiling here, it's not even going to show up because we kill it before it even does the print, right? What about the key being a slice instead of an allocated string? So it could be a slice for the purposes of equality comparison, not for the purposes of ordering, right? So you couldn't order these by their byte value, but we could keep them a 53. So there's like, in fact, it is slower, but at this scale, like 52 versus 53 is just like different in this particular execution. So I'm going to keep this the way it was, and we can come back to optimizing if it turns out to be a problem. So B-tree map, because this is very straightforward, right? So I'm going to keep it that way. But so UTF-8 parsing is known to be pretty painful. We're already getting this with lines because line gives us a string. But what we can do here is say, this is going to be a vec of U8. So don't bother trying to parse out the bytes here. And then we will do, instead of lines, which requires you parse as a string, we will do, what do I have? Git diff. Okay, great. I will do split by new line. Now, this is already broken, but I'll explain why in a second. So now this will be a vec u8. We'll split once by a literal semicolon, which doesn't exist on slices yet, which is fun. Do we have an R split? Yeah, so this now needs to be fields is this, and then in fact it's R split n of 2. For the same reason that new line is broken, this needs to be R split 2. I'll get to it in a second. So the temperature is going to be fields dot, does this yield them in backwards order? It starts at the end of the slice with the match element, last element if returned. So does this... it returns them in forward order. Okay, so station is fields.next.unwrap and temperatures fields.next.unwrap. Like so. And then it is unhappy because the n needs to come first. And this needs to be this. Oops. And now it's unhappy about this because this is now a slice of U8s and parse expects to operate on strings. So we'll do std from UTF-8 of temperature unwrap because we know that this is valid UTF-8. We've been told that that's the case. And here, this is now to vec instead. So we're avoiding the UTF-8 parsing for everything except for the temperature. Only the temperature we're going to UTF-8 parse. And then only down here, when we construct the B-tree map, we need to map. So we're going to get the key and the value. And we're going to have to map the string from UTF-8 of key and then value. And again, we're going to unwrap because it's all valid Unicode. Yeah. I'll explain why this is broken in a second. I just want to start the run. Oh, parse float invalid. I think I messed this one up. I think maybe these are in fact reversed. Great. Okay, so the problem here is that in UTF-8 encoding of strings, the way this works is anything that's ASCII just stays the same in UTF-8. It's a single byte, and it's just the one byte that is that character. So a new line, for example, is 0A, I think, in hex. And so you, like, if there's a 0A in the byte stream, you would assume that that means new line, because a new line, if you have a new line from ASCII, like the actual new line character, it is encoded in UTF-8 as hex 0A. The problem is UTF-8 is a variable length encoding. And so there is, there's one byte in the there's one single byte in the UTF-8 encoding that says this is a multi-byte character, or character is the wrong word, but basically. The problem you run into is that if you have that character that says this is a multi-byte character and then a new line, then that means a different character. It doesn't mean a new line. So if you just look for 0A in the byte stream, you have to look back to see whether the previous character was an escape. The same is also the case, like UTF-8 does not just have to be 2 characters, it can also be 3 or 4, depending on what that first byte is. And any of those could be a literal 0A hex, and it wouldn't be a new line. It would be some longer byte sequence that represents a Unicode character that just happens to have the bytes 0A in them. And so this is why this code is actually broken. Like, this is just incorrect, both for the new line. If we split by new line, we might now split in the middle of a Unicode character, and for semicolon, because the semicolon is also just 2 hex characters. I forget what they are. But so if we look for that Unicode character, if we look for that byte, it might just be that that byte appears in a different Unicode character. Now, for this particular input, I don't think this actually occurs, but that doesn't matter. We've been told arbitrary UTF-8, and so that is what we have to deal with. The continuation bytes always have their highest bit set. Is that true? Let's go look at UTF-8 continuation. Or Wikipedia, maybe. yeah, so these are different UTF-8 encodings. So we can have, right, so this would be anything that's ASCII, right? So the first 128 code points. Then if the high bit of byte 1 is 1, then it means it's a, I'm encoding bits I'm encoding parts of the code point in the subsequent bytes. But all of these have to start with 1, 0. Interesting. So they can't be ASCII. Okay, so that saves us then from this problem. This problem does not occur. Nice. Okay, cool. Ignore me. We're fine. So this could be a danger, but is not. Good catch, chat. All right. But interesting, though, is that this didn't save us any time. We're still spending about 50 seconds. So not doing the Unicode decoding here didn't really save us anything. It saved us, we still have to do the decoding here, but not doing it for the station names didn't make a difference, which is fascinating. But even so, I think we should keep it because we're clearly doing strictly less work, right? Let's do lazy Unicode. Oh, unchecked, you're right. Let's do unchecked. And same thing down here. And then we don't need the unwrap. Safety, the readme promised. We're in performance hacking here. This is okay. All right, let's see. You know, when the readme promises, that's all we need. We know we're in good hands. So the difference between the unchecked and the checked version here is the checked version will walk the byte sequence and check that it's valid Unicode before, and then return a result. That means it's still doing the Unicode decoding. So Chad is totally right. This needs to be unchecked, which is really just saying, trust me, these bytes are UTF-8. You don't have to go check, is what we're telling it now. And so now we should actually not be doing the Unicode validation, and we should see now the speed up. 47 seconds. Okay, so we saved 3 full seconds on the walk here. Wow, that's wild. Such a speed up. Chat, we did it. No, I see no problems. Great. So we'll do a git commit a amend. And then someone said, how about we get rid of overflow checks? Let's see. I doubt this will make much of a difference, but you know, if we're really going for it. Oh, trust me, we're gonna get into byte searching with memcar and SIMD, and we're gonna get to all the good stuff. But we're starting slowly. It's a gentle introduction, you know. So now we're gonna do. Okay, so we're doing. Without overflow checks, I'm guessing this will save like... I don't think this will save anything, actually. I think this will be the same time. And yes, overflow checks should be off in release mode anyway. Yeah, exactly, same time. So we're going to leave this out because it's in release mode anyway. All right. Okay, so let's now think about what do we want to do next. Well, one thing that's bothering me here is this reading, because we're taking the file and then we're reading it in like smaller chunks, but we know we're going to walk the whole thing. So what we actually want to do is something called memory mapping, which is you tell the kernel, hey, can you just make this whole file be present for me in memory? The way you would normally do this in Rust is through something like the memmap crate, which allows you to do exactly this. It lets you take a file you've opened in Linux and then memory map it into our thing. Now, this is technically an external dependency, and I said no external dependencies. So I'm gonna disallow us from using this, even though it would save us a bunch of time, because it lets us talk about what memory maps are and how you use them. What we're actually going to do here is instead look at what would happen if we do, so you'll see here, there's an mmap as raw desc here, which is really just implemented for raw FDs. The thinking here being that if you have a file descriptor to a file, that's all you need in order to tell the kernel to do this operation. And so let's look at what they do when you do a map. What does mmap options new? Okay, that's unhelpful. And then map. So let's go ahead and find a mmap options new, which is just default. Cool, thank you. And then it does map, which is the thing that we want. So it gets a raw descriptor, and then there's mmap inner. Oh boy. Okay, let's go actually look at the source here. Source Unix mmap inner new. Okay, so it computes. You'll see here. It gets the length of the file, and then it passes that in as length here. File is going to be the file descriptor. Flags, we'll talk about flags a little bit later. And then the offset into the file you want to start reading from, that's going to be 0 for us here. Okay, so the alignment here is just based on the offset, which we don't care about. Adjust mmap params. Let's go look at what they're doing over here, just to see if there's anything we want to keep. Not worried about, we're hyper optimizing here. So we don't care about 32-bit targets. We're just going to say 64-bit targets, so this can't happen. Length is length plus alignment. Our alignment here is always going to be 0 because our offset is 0. So that can stay the same. It's not going to be 0 sized. Okay, that's all it's really doing. And then you'll see it calls mmap here. Mmap comes from libc. Now, libc, I think, is a dependency we have to be allowed to take because it's libc. I'm gonna claim libc is allowed. Libc is also used by the standard library, so we're not actually taking an extra dependency here, because otherwise we would have to do like raw syscalls, and that feels excessive. So this is the main thing that we need here, and I'm gonna make this slightly nicer. Mmap. And it's going to take a file, which is one of these, and it's going to return you a static U8 slice. Maybe not static. We'll find out. Oops. No. What did I do? Oh, I did something stupid. I don't understand what I did. Okay. F file returns you a static U8 slice. Okay. libc mmap. This is going to be a pointer to null mute because we're not trying to map into a particular area of memory. We want the kernel to tell us where it mapped this. The length is going to be f dot f dot metadata dot unwrap dot length. So that's going to be the length here. The protection bits. So the protection bits, you'll say is here desk.0. What? Second argument to map new. Yeah, that's just down here. File is going to be f dot as raw fd. The protection bits are, you can basically set whether this page, whether the mapping of the file should be read-only or allow writes and so on. So let's go ahead and look at what we do for the protection bits. In our case, all we need is read access. But let's see what the default here is for self.populate. Let me go ahead and look at the default they have for mmap options. They derive it, so populate is false. So populate is false. Okay. Oh, I closed that, didn't I? Okay. Mmap inner. Create OS. Where is the... if populate map populate. Okay, so they set populate to 0. So we just want protect read. Yep, and we want map shared. We don't care about no reserve, and we don't care about populate because we don't want to pre-read the whole file. We do, however, want to do one more thing, which I'll show you in a second. Cool, and then the offset is going to be 0. So that's going to give us a mapping back. This is going to panic. Otherwise, they have a from raw parts, which is really just a pointer that has the offset added in the length. So this, in our case, is just going to be a pointer, and we're going to do stud slice from raw parts. Now, there's a bunch of reasons why this is broken, but let's have it be fun for now. Cool. This pointer is a pointer to a C void. Len here, we're going to cast to a U size. This we're going to cast to a const U8. And this is going to be std IO error last error. Now, technically, this isn't static. Technically, this reference only lives until this file is closed. So I think actually what I'll do is this. Yeah. Okay, fine. I'll align the lifetimes. That's fine. That's fine. Okay. All right. Cool. So now what we can do here is we'll still open this, but then we'll do map is mmap of f. And there are a couple of other things you can do that are neat about a mmap, which is you can also tell the kernel how you're going to use it. So you'll see here, not on there, but on their mmap type. How do they expose it in this library? Yeah, so you have this thing called advice, where you can tell the OS how you're intending to use this. And in particular, there's one thing that's really neat in here, which is the ability to tell it here. Where's their definition of advice? Here. Okay, so you can tell it that you're going to read the file sequentially. And what that means is you tell the kernel, hey, for this file, when I read at a given byte offset, I'm going to keep reading in that direction. So feel free to fetch more of the things for disk from me in advance. And so we're going to tell it that we're going to do this, this sequential reading. And you do this through a separate call here called libcadvise. We're not going to do an offset here because this applies to the whole file. Actually, why do they even pass an offset? Yeah, offset 0. All right, that's fine. Because you can say for this part of the file, I will read it sequentially and stuff. It doesn't matter to us. In our case, we will just say here, we'll do that here as well. libc advice of pointer, and for length len, we're going to advise. Let's see, is it in libc, I wonder? Advise sequential, which is 2. Why does the libc... Okay. Cool. Like so. And then we will actually do... There's no real... this. All right, so now we get a map back. We now don't need the buff reader anymore. And we can actually, we could still have a buff reader over the slice if we really wanted to, but there's no real reason to do that. This is now just going to be over map. Split is going to be by C equals new line. There's no unwrap anymore. And this needs to be a star. The other thing that's neat is now we don't even need to allocate vectors, but let's do that as a separate optimization path. Okay, let's see. Let's first see whether that's any faster. So remember, we're comparing to 48. So we'll run that. All right, what is chat asking? What is the difference between M mapping and reading the full file into a U8 vec? Isn't that just basically the same? It's similar, except A, you don't need to keep a vector of the whole contents of the file, right? So if you do that, you would need to read all billion rows into memory, which means you're allocating that much memory. You don't need to. If you instead just know that you're reading through the file sort of sequentially, then you can deallocate the things that you've passed by. Whereas with a vector, you're going to have to keep doing the allocate a vector of twice the size, copy over the things each time you go over that increment. Ooh. Interesting panic. Well, we'll look at that in a second. So you don't have to do any of the sort of grow by 2. You don't have to do any of the copies. You can deallocate more eagerly, and so you don't need to have quite as large of a memory use. But also, you're giving a clue to the kernel about what you're going to do in the future. Because the kernel now knows, A, that this is a memory mapping of this file. It doesn't if you're doing... just reads, and B, with the sequential flag, we're telling it where we're going to read in the future. So it gets to start loading things from disk in the background while our program is running. So we get effectively IO parallelism. So like mmap doesn't actually copy everything in memory. It's more of a, like the kernel makes it look like that's the case, but the kernel owns that mapping. Closing the FD doesn't do anything to the mapping. You must unmap if you want it gone. Oh, even better. Okay, so this doesn't even need to be tied to anything. Cool. This now fails at here. Interesting. Why? I'm going to do... I'm going to do this just to give us slightly more information about what's happening. It's unchecked of line. Yeah, and with mmap, someone also pointed out, with mmap, you could even map a file that's larger than the amount of memory that you have. Whereas when you read it onto memory, that wouldn't work. So like, it's not allocated in kernel memory either, to be clear. It's memory mapped, so that it's not, all of it is not stored in memory. It's that the kernel makes it look that way by configuring the virtual memory system in the right way. The way it actually works is it maps only certain pages at a time. Oh, let's see, bad line, empty line. Oh, it's because there's probably a new line at the end of the last line. So here we'll do if line is empty, then break. The actual challenge assumes the file is placed in a RAM disk because it's already in memory. Even then, you would, if you're doing this with a buff reader, even if it's mounted on RAM disk, then you would still be copying all those bytes into your own memory into a separate vector, right? Whereas with the mmap, the kernel will realize that these are the same and not have to do that. 32 seconds. Okay, cool. This is definitely faster. What do we have here? So now we have git commit mmap. 32. Okay, that's a lot better. And remember, we're still running single core. We haven't done any multi-core parallelism. One of the reasons for that is because once you do that, it becomes much harder to figure out where you're spending your time because all the threads are doing things concurrently. So this is on purpose that we're doing the single core version first. There's another optimization here, which is we can, and in fact, let's perf record just to demonstrate that I'm data driven here. So we'll let this run for a little bit. Perf report. Let's see what perf report tells us. Okay, we're still in main. I'm still not getting libc symbols, which is very disturbing. Okay, where's our time spent? Okay, we're spending a decent amount of time, 10% of our time now, parsing F64s. 5% in splitting here. 2% in splitting here. So definitely some time spent on the splitting by new line and splitting by semicolons. Hash maps. Yeah, so this is doing the hashing and then this is doing the lookups in the hash map. So there's some time going here, but still only 70% is going to main. So where's the rest going? This seems like we're losing some of our stack information. And so I'm going to do one more thing in our cargo config, which is I'm going to do, what's it called in the Rust configuration? It's called, is it called emit frame pointer? No, it's called force frame pointer equals yes. I believe. So we'll run that for a little bit. And we'll kill it. Let's see if that gives us a more reasonable report here. Aha, now we have 99%. Okay, so what did I do? Force frame pointers. So when you build programs, there's this thing called the frame pointer, not when you build them, but when you run your program, there's something called the frame pointer. The frame pointer is a register in the CPU that points to the, well, no, it's not a, there is a register in the CPU that's the frame pointer, but the, let me change my definition here slightly. Maybe I'll do this with drawing now that I think about it. I will do this with drawing. We haven't drawn in a while on stream, so let's do that. Okay, so when you call a function, there's something called the stack. Ooh, that's definitely not what I want. Give me a slightly less insane brush, please. Less insane brush, please? No? What? Why is my brush selector not working? Ah, come back. Why? Okay, fine. I will do this. So, okay. All right. Everyone settle down. Brush. I want to select my brush. Okay, I think this program may have some trouble. Okay, maybe I will not draw this then. I know this program hasn't been updated in a while, and it's showing. All right, fine. We will not do it with drawing. I will try to explain instead. So when function A calls function B, normally in execution, there's a bunch of stuff that happens in the prologue of function B. So this is before the body of function B is executed. We go into what's known as the function prologue, and then function B executes, and then we go into function B's epilogue, which is code. Like the prologue and the epilogue are injected by the compiler to do the things that are needed to like call functions and return from functions at the CPU level. Like this is sort of this is the calling convention. This is how does, for example, a function know where its arguments are located? Like how does, like when A calls B and passes a bunch of arguments, where do those arguments go? And the calling convention dictates that some of them go in CPU registers, some of them go on the stack, and they're placed there by the function prologue. The epilogue similarly dictates where the return value goes, and also does the instruction that's needed to go back to A if A called B. So this is the ret instruction, for example. Now, as part of the sort of function prologue and epilogue, there's an optional step. The optional step here is to put on the stack a pointer to the previous stack frame. So when A calls B, the question to ask is, do you also push a pointer to where A's stack is, or do you not? And this step is optional because, technically speaking, you can when if you're at the top of B's stack, like B is currently executing, technically you can figure out where A's stack is through the debug info, because you know the size of all the arguments, you know where they're supposed to be passed, and so you can just like be at, okay, my pointer to B is here, and I deduct all the information that I know should be on the stack according to the debug, and so therefore A's frame must start here. This is a bunch of work though, and this tracking doesn't work perfectly, and so sometimes you don't realize where A's stack frame starts, or it points to the wrong place. And so this matters when you start unwinding the stack. And unwinding the stack is exactly what happens when you try to construct this kind of thing. It's that when you do when you record through perf, for example, it samples every now and again. It checks your program of like, what is it currently executing? And that question of what is it currently executing is which stack of functions is this thread currently in? In order to figure out that, it needs to walk the stack to figure out which function call chain the program is currently inside of. Now, that walking is more difficult if you have to rely on the debug symbols, and it's much easier if you have the frame pointers. Now, the reason people don't have frame pointers in like modern programs, or why they're often off by default, is because there was a period of time where CPUs had a limited number of CPU registers. So every register was precious. You'd wanted them to use for compute, not to use for things like frame pointers. But in order to push the frame pointer onto there, you needed a register to pass the frame pointer in. And there's a bunch of details here that we can mostly ignore, but it comes back to the fact that there was a period of time, especially with 32-bit processors, where registers were precious, so we didn't want to use them. And because it's usually possible to unwind the stack without using this register for the frame pointer, well, then we're just not going to use it and use that for compute instead. There's been a bunch of experiments since then that shows that on 64-bit processors, which have a lot more registers, you don't need to do this optimization. You can just always put the frame pointer in there, and then unwinding is always perfect because the information is stored there. You don't need any heuristics. You don't need the debug info. But the defaults haven't really caught up. Now, there has been an effort to change the defaults so that this is like, so that we get the frame pointers and always get perfect unwinding. But Rust, for example, does not default to this being on. I think it probably should. There's actually an ongoing discussion on the Rust issue tracker for whether we should change the default here. And I think the default has now been changed for stud, but has not yet been changed for crates, or it's the other way around. But this is like a thing that I'm guessing will probably change because it makes debugging much better, and it doesn't really make programs slower, at least in the vast majority of them. They don't have unlimited registers, but they have a lot more. So the reason I turned on force frame pointers is so that now my stack trace doesn't have any gaps in it. And so I can actually look through this whole thing, and now you'll see the whole stack call chain is all perfect. Okay, so we'll see 10% of our time in parse, tiny bit in max and min, decent amount in alloc here, hashing, lookups. What's interesting to me here is there's nothing here that shows that we have to do the allocations for each key. And I think the reason is because we only do that allocation if the entry is not already in there. So only in this case do we turn it into a vector, and we only drop the number of unique keys. But we can now do this. Do this. Because these can be references into the mmap. There's nothing that needs to be owned about them. And so now this can actually go back to what it was, because we always have the owned version, like so. And so this is sort of a neat thing that makes the code nicer. And now this can be stir from UTF-8 because it doesn't need to be a string anymore, because we already have a reference. Now, this is something where I don't think this will actually make a difference. Like, what was our previous run here? If we go back up, our previous run was 32. This will probably not make a difference because we're still at 32 seconds, which is quite a long time. And most of the keys don't need to do this allocation. Same thing with the strings at the end. Like, allocating those strings, we're only allocating less than 10,000 strings, because it's just the number of keys in the map, number of unique keys in the map. So this, I think, is not going to make a difference, but it is something where, yeah, like effectively the same number. But as we optimize the rest of the code, this matters. So I'm just going to do it proactively, even though I know we should be data driven. This is a premature optimization, but I'm going to do it anyway. Okay. Less allocation, please. Doesn't this break the sequential read assumption? Not. Ooh, that's an interesting question. That's an interesting question, actually. Yeah, no, you're right. Let's undo that. I don't know if you're right, but I agree that I want to measure it. So let's do, maybe make the key, but measure, since we're breaking sequential. It'll still be in the kernel page cache, but that means that we're holding up basically a random set of pages because we happen to have keys to them. And we're going to be accessing them every time we look through the map. So the kernel is going to have to keep those pages in memory. There probably aren't that many, so it's not using that much of the memory, but given it doesn't even show up on our current allocations, I think let's keep it. Okay, so let's do this. Let's do frame pointers, please. Okay. What do we have next? So in our perf report, what did we get? Where else were we spending our time? Well, in here. Main. We're spending a decent amount of time here parsing floating point numbers. And that's sad. We don't want to spend that much time parsing floating point numbers. So how about we do something better than that? Well, remember how there are floating point numbers with a single decimal point? Well, those are just integers shifted by a power of 10. So how about we do, instead of parsing them as F64s, we parse them as I16s. So this is going to be a little interesting because we have to skip the dot. Now we could actually implement this parsing ourselves by saying temperature is 0. And then we're going to do sign is going to be temperature 0 is equal to minus. Actually, we're going to do temp is going to be temperature iter dot copied, because why not? They're bytes. And then trying to decide how I want to do this. There's a stupid simple way, which is you just branch on whether the sign is minus or not. There's also a way in which you don't do a branch at all, but how about we do it the simple way first? So we say if it's 0, if temperature 0 is this, then temp is temp dot skip 1 else, which actually means we can do skip one else 0. And then we're going to say temperature is 0. And then for, we know it's always exactly 3 digits. So we're going to do for I in 0 to 3. The reason we want to use the explicit loop iteration here is because then the compiler can do loop unrolling, right? We tell it how many characters it is. We know it doesn't have to count. And then we will say temperature times equals 10, right? Because it's times equals 10 from the previous number we're at. We're shifting the previous number left. And then we will add temperature. Actually, for I in, we have to be slightly more specific than this because it's going to be 0, 1, 2. No, 0, 0, 1, 3, right? Because we're after the minus sign, potentially minus sign. We want the 2, remember, it's between minus 99.9 and positive 99.9. So we want the 2 whole parts of the number. And then we want to skip the decimal place. And then we want to get the character after the decimal place. And we're going to just treat that as though it's a 3-digit integer. So plus equals temperature of I. This one can also be no bounds checks, but that's fine. We're in release mode anyway. Right. And now this is going to be I16 max, I16 min. This is now going to be I16, I16, I16. And in fact, I don't think this is right. This is skip is what this should be. This is like the offset. And we want here skip plus I. And this needs to be t so that we don't alias the value. This is a U8, which we're just going to cast. No, which is this is a character. So this is going to be minus B0, right? So we're going to subtract out the ASCII value of 0 from the ASCII value of the digit we're looking at. And that gives us the actual numerical value. And then this whole thing, we're going to cast to I16. This is now actually 0. This is going to be of t, this is going to be of t, and this is going to be of t. But the accumulator here probably needs to be more than I16. This probably needs to be an I32. Because if you have enough rows, and we're adding them together so we can eventually take the mean, then this needs to be... this might overflow in I16, which is only 65,000. So if you, given the number of rows we have, I think realistically this needs to be a bigger, like the accumulator needs to be bigger, which is fine. This can just be I32 from. This similarly can be I16 from. I tend to prefer using the from implementations rather than casts, because from, for things like this that are infallible, from just means that like statically when you look at the code it is infallible, whereas the cast is allowed to be lossy. This is not allowed to be lossy. And then down here the printing is going to be a little weirder now, because printing this will actually be turning it back into a floating point. 164? You think it needs to be I64? Unsure. I guess we could do 64. I don't think we'll need 64, but all right, fine. Yeah, the printing is a little trickier because we now have these integer values that we need to print as decimals. We could cast them back to floats and then print them. Which, given the printing is cheap, maybe that's what we do. So this would be min as f64 divided by 10. Max as f64 divided by 10. And this has to be sum as f64 divided by 10 divided by this. Yeah. Oh, right. And we're missing, yeah, we're here also missing, t dot, if skip is equal to 1, then t is minus t. And this is where we're going to get into branch prediction problem, but we'll get into that later. What did I mess up? Oh, this needs to have a colon. This needs to have a colon. And all right, let's see what we get here. Nope. Len is 3, but the index is 3. Ooh. Interesting. In release mode? Interesting. Well, that's interesting. Oh, it's because... Okay, we can't actually guarantee this because... because it's not guaranteed to have two whole digits, right? 9.3 degrees is not 9.3 degrees. It's not zero padded. So yeah, okay. We could actually walk from the back here. I think walking from the back here is actually going to be easier. In fact, it's going to help with the skipping here too. So, okay, t is going to be 0. Then we're going to do for I in 0 to 4. No, in... Let's just do for I in temperature. Let's see how the compiler does with this. So we're going to say... we're going to walk from that side. We're going to say if I is a dot, then we're going to skip. And yes, I know this branch predictor will probably be sad. And then we're going to add, we don't need the skip anymore. And this is not I, this is now D for digit. And then this is going to be, we need a mul. So 1 small mul times equal 10. Right, so we walk from the right, we take the digit we have, we multiply with the multiplier, which starts as 1, and then will become 10, and then will become 100. So we take the first digit, multiply it by 1, which is just the digit, add that to t, then we go around again. We're now at the next character going back. This needs to be .iter.rev. In fact, this is going to be a match on D, where if we hit dot, then we continue. If we hit minus, then we break, and we say t is minus t. And otherwise, we do this. And this needs to be this. And now this all goes away. Middle out, yeah, that's funny. The other way here, right, would be to look for the dot, parse as I64 using the standard Rust parsing logic, and then parse the fractional digit, which we know is always there. I'm not convinced that's faster. It sort of depends on how complex the Rust parsing logic is here. And then it would be nice if we could tell the compiler what we know about these numbers, right? The temperature is always at least 3 digits. But let's see here what we get with this. Kirby. All the numbers have a dot. Yes. We could match on the length of the slice. but that doesn't tell us whether there's a dash as a negative or a missing digit. Right? So minus 9.3 is the same number of characters as 99.3. Cool. This now ran in 30 seconds, so not really any faster. Let's do a perf record of that and see what we get. Let's see where this time is coming from. Obviously, a lot of it is still the hash map. The split and the R split. But I'm not really seeing anything spent on parsing. So the parsing time is now basically gone from here. And yet we're no faster. Interesting. Yeah, like 10% vanished, but we weren't 10% faster. But it could just be luck of the draw or the lack thereof, right? Oh, there's this iterator, which is the iteration from the back on temperature. But that's like adds up to 1% of execution time. This is also the kind of stuff that you can pull out with some tools like Hyperfine, right? Which will run it multiple times, try to gather some information. Oh, it's because it's inline, right? So the cost is still there. It just doesn't show up as the... yeah. So if we go to main... No, here. What? No. I see. It's self cost on main is what's gone up. Yeah. All right. There is a... So you can also go here and then say annotate BR main. And then it will show you the actual assembly for this function and which specific instructions are causing you this cost. Now it should also give me the source annotation, but why is it not? Oh, is what I want. That's entirely unhelpful. Why isn't it showing me the not line number, source code view? Yes, there we go. Okay, so here we now have inline the all of the Rust code that's actually being called in here. And so if we now go up, where's our reset? Here, this is what I wanted. Okay, so if you squint between the lines here, you'll see that we're currently in main. Might be hard to see because it's inlined everything, right? But you'll see some calls that are familiar, like here's our I65 from and so on. And you'll see if predicate, yeah, here 4D in temperature. And so you can see where all of the time, like percentage time for each assembly instruction comes from. And this comparison here on D is certainly where some of the time is coming from. We are, however, getting to the point where looking at the assembly instructions is sort of misleading because also where the CPU, like which part of the CPU you end up actually spending the time for. So what I mean by that is like this jump is expensive, but why is a jump expensive? Like what is the CPU doing that is expensive here? And this is where you get into things like branch misprediction and prefetching and all of that stuff. And what you can do is perf... Oh, I never remember what this is called. It's like perf stat something. Perf stat perf stat. What's the one I'm looking for? Maybe I can just run it with this and see what it gives me. Yeah, so here you'll see it shows, this is like, we're not giving a line by line view here or a function by function view. Instead, we're getting information about how did the CPU spend its time? Like, where did the time go? And you'll see we run 3 instructions per cycle, some amount of stalled cycles. So stalled cycles are when the CPU wanted to run something, but it couldn't because the data wasn't available yet because it still had to be fetched from memory. You'll also see, yes, we have spent like about 8% of the CPU is just idle because it's waiting for things. The number of branches per second, this is a lot of branches, right? We're branching 3 billion times a second. Branches are expensive because the CPU, ideally, it knows what the program is about to do. And so it has like multiple compute units in there and things that can access the memory and things that do floating point operations. And ideally, you keep all of those active at once. The way you do that is, instead of just executing the next instruction, you execute like the next 10 instructions all in parallel because you're using different parts of the CPU. But when you have a branch, so like an if this or that, then the CPU doesn't know which branch you're taking. So it doesn't know which code to run next. So what the CPU will usually do is it tries to guess which branch you're going to take based on which branch you've taken in the past. And so if it, let's say in the past you took the A branch, so it's going to start executing the code in the A branch. By the time the result of the branch is known, because again, remember it's running multiple things in parallel, when it knows the result of the branch, if it mispredicted, so if it predicted A but it actually took B, it has to throw away all the stuff it did in the A branch and now execute the stuff in the B branch. So this is a misprediction. When you have mispredictions, then you end up with exactly this problem of the CPU now needs to like scrap a bunch of work that it did, so those CPU cycles were wasted, but also it might need to wait for things that need to be loaded in this other branch because it didn't load them, because it didn't think it was going to have to do this. And so this is where you have this thing called the branch predictor that tries to keep track of these branches and which way you take. But usually, if you have branches that are highly difficult to predict, things like, is there a minus sign at the beginning of this temperature, which is going to be like 50-50, then the branch predictor is often going to be wrong. And so we are often going to throw away the cycles. And you'll see here, it mispredicted 2% of all branches, but that's not super helpful to us because the challenge we run into here is not how many percent of all branches, is that if there is a branch on the critical path of the program, like that we execute a lot very frequently, then mispredicting that branch, even if it's only one, might cause a lot of stalls and a lot of wasted cycles. And chat pointed out you can do -D to get more stats out of here. So we'll let that run for a while. There we go. So now we get more stats. You'll see here, this is how often do we load stuff and we're able to get it from the cache that's closest to the CPU. How often do we miss in that part of the CPU? We're going to ignore this for now. This is like stuff around the page table and when you do faults and all that stuff. I think we can mostly ignore that right now. But the branch misprediction here is a little bit sad. The other thing that we saw out of the, and I think that mostly comes from this parsing. The other thing that we saw from our perf report was that we're spending a decent amount of our time down here in the split and the R split. So the parsing out of the new lines and the semicolons. So we kind of got to pick here which one we want to do first. Do we want to try to speed up the stuff around the parsing, which remember was about 10% and is probably still about 10%. It's just, it doesn't show up as a subfunction. In fact, maybe let's make it a subfunction so it will show up. Let's do that. So fn parse parse temperature, which takes a temperature, which is a slice of U8s, and it gives you back an I16. And then we take all of this stuff. This goes away now. We do this. Stick that into there. This now returns T. And then we say here, let T is parse temperature of temperature. All right, let's see what we get out of this. So we'll let this run for a while. And now we'll do perf report, see what we get out. Yeah, okay, so our parse temperature, which is inline, useful information, is about 8% of execution time. So we didn't really save very much compared to the 10% that was floating point numbers parsing. We saved a little bit, but not all that much. And if we look inside of this, it doesn't really tell us where that time is going. Although we could here, no, that's fine. Okay, that's fine. I now want to, oh, why won't, oh, because it's inlined. Yeah. Can I still, yeah, that's what I worried about. We can here, if we really want to, do a inline never. This will make the program slower, but it will also allow us to introspect specifically the assembly of that function to look at where is it spending its time. This might not be super useful, but let's see what we get out of it anyway. So if we go in here, find the main, parse temperature, and I want to annotate this with source. Without source maybe, with source. So let's see where this time goes. So parse temperature does add. So this is just the adding of the indexing into the temperature array. Then the partial eq for the pointer. Yeah, so this is the termination check for the loop of have we reached the end of temperature, which I actually think we can omit entirely because we can instead just loop over a particular set of numbers. We can just loop over the indices directly. So this we can probably eliminate entirely because we already have an explicit break here when we hit, oh no, we wouldn't know because there might not be a minus, in which case the way you know is you at the end of the, or the start of the thing. But this feels like a thing that can be optimized. And then, yeah, this is the iteration from the back up here, right? Because we're decrementing the pointer, we're moving from the end. And then here we have our jumps for matching on D. And then we have, yeah, the multiplication and the adding, which takes some time. And then we have the jump back up. So yeah, so we have a decent number of these like jumps and branching instructions that are unfortunate. This jump shouldn't even be needed because we should be able to unroll this loop, at least in theory. Yeah, let me think how we want to do this. But I think so the question still arises, right? Like, do we want to spend our time optimizing parse temperature first? Like, I think we're going to do both, right? Do we want to spend our time optimizing parse temperature, or do we want to spend our time optimizing the parsing of the sort of extraction of the delimiters? I think maybe let's switch gears for a second and go do the delimiters. Yeah, let's do that. Okay. So let's leave parse temperature there. We'll come back to it later. Temperature as int. And now let's figure out what we can do about the splitting. So one of the things that's annoying about split is that it walks character by character and compares them using a closure. That's fine if you don't care about the performance, but if you care about the performance, this ends up being very, very slow. So what are ways in which we can do it better? Well, there are a couple. So one of them would be to use something called memcur. So memcur. This is basically a super optimized function for finding the first occurrence of a character in some sequence of bytes. And it does this with like SIMD and everything, so it's super, super fast. Now, there are other ways to do it, such as basically implement memcur ourselves. I forget whether libc comes with memcur. Yeah, it does. Okay, so let's do it with memcur first, and then we'll see what we get to. So the way we're going to do this is we're going to keep track of where we're at, and we're going to keep track of, that might actually be all we need. And then this is now going to become a loop. And inside of this loop, we're going to call memcur, which takes three things. It takes the string that we're trying to parse. So in this case, that's going to be or the slice that we're trying to parse. That's going to be map, but it's specifically going to be map starting it at, right? Because that's where we're currently at. We don't want to search from the start of the file. Then this is the character, the byte that we want to look for. In our case, that's going to be new line. And then n here is the length of the map. So rest here is going to be map at ... And so here we can then say this is going to be rest, and this is going to be rest.len. And what it returns is a pointer to where, I think it's where that character appears. So next is going to be this. Next line. This is really next new line. And if we look at the documentation here for memcur, you'll see that the down here, it's against the initial n bytes of the memory area. Both C and the bytes of the memory interpret unsynced car. You can also search backwards from the end, which is not what we want to do here. It returns a pointer to the matching byte or null if the character does not occur. And so what we want to do here is we want to look for the next new line. We want to say that the line is... actually, we want to say... a couple of ways we could do this. I think we're going to say... line is going to be trying to decide how I want to do this, because if next new line is pointer null, which I think it's a pointer, right? So we can just say is null. If it's null, then I think we want to, we like sort of a loop inversion we're going to have to do here. So the line is going to be all of rest. Otherwise, but we also are going to have to remember to break after this, right? So there's slightly more than this. The else case here is going to be, actually, no, we can leave this to be the break because we know that there's a new line after every line, which means that we should always find a new line until we get to a line that's empty that makes us break. So we don't need to remember to break, since next iteration we'll find empty line. And in the else case, the line is going to be, actually it's not even rest, right? It's rest. Yeah, no, that's right. And here at is gonna get added to line plus 1. So skipping over the line we found and the new line. Okay, so the line is, if we found a new line character, then the line, no, if we didn't find a new line character, the line is everything from where we're at to the end of the file. Otherwise, it is from at until, and this is where it'll be slightly annoying because next new line gives us back a pointer. So in this case, actually, maybe we walk this instead of by index, we just walk it by pointer. I don't love that. But maybe that is what we do. But this will actually be... we have to compute the length using next new line offset from... And this needs to be as const u8. We want the offset from rest.asPointer. Right, so this is the distance between the where memchar returned and where it started searching. So that's the length of the line. And then we want rest to be no, that's not right. It's the offset from... Yeah, no, that's the offset we want from here. But this is going to then include the... Yeah, and this is not going to include the new line character because this gives us a pointer to the new line character, which we're ignoring. And that's why at is going to add both the length of the line and 1. So then this is going to be... Why is this unsafe? Like, what? Offset from unsafe? All right. Safety. Memchar returns pointers in rest. Always returns pointer in rest, which are valid. It's unhappy here because this is supposed to be a libcc int. And then it's unhappy because this safety rest is valid for at least rest.len bytes. And this has to be as pointer. And as c void. And really this should be cint. We should really just import these because we're going to use them in a bunch of places. And then it's unhappy with me here because what's returned from here is an I size. And we happen to know that it is a... we happen to know that next new line is always greater than the pointer we pass in, as we know this is positive. So we know that this is, we can just cast this as usize. And then just as a sanity measure here, I'm going to do this. Because this feels very brittle, which is all the more fun. Unchecked. Yeah, that's fine. Unsafe. That seems pretty promising. Right, I'm seeing 1 point after the decimal. I'm not seeing a new line inside the string, so I think we got that right. This only got rid of the new line scanning that we're doing, right? So now we do the new line scanning with memcar. Let's see what we get out of this. And so in theory, this should be what, 8% faster or something? Okay, 28. Hard to say whether, like previously we were at 30. So 10% of 30 is 3. So it should be about 3 seconds faster, right? Little less than 3, 8% I think was the search for new line, if we eliminated it completely, which we didn't. So a saving of 2 seconds is actually about what we expect here. Let's do a second run just to see it in action again. 28. Okay, so pretty consistently a few seconds faster. So that's nice. So git diff. Let's see. I want to get rid of... Oh, this has to be that. Just wanted to see if I could get rid of some of these imports, but maybe not. Memcar new lines. Okay, so that's one of the searches. The other is this look for semicolon, right? So semicolon is also something we're trying to look for very quickly here. Now here we could also use memcar, but we could also use SIMD because that seems like fun. Why not? So I think I am going to use SIMD here. What we're doing is, we know that this line, line is at most 100 characters for the station name, was the max station name, plus 1 for the semicolon, plus at most minus 2 digits decimal point fraction. So plus 5 is 106 bytes, right? Now, 106 bytes, if you count it in U8s, is, well, it's 106, it's length of 106. Now, if we go to look at the stuff we have in the standard library for SIMD, you'll see that there is a U8 times 64 is the biggest we have here. So a SIMD vector with 64 elements of type U8. Now, I think... Oh, so maybe we can't use portable SIMD. That would be pretty sad. We might then have to use the Arch ones, because I think there is a... Oh, no, I have to look at intrinsics. SIMD. I believe I want SIMD. Where's SIMD eq? SIMD eq. Well, that's unhelpful. What if I just look at the SIMD crate to see whether... Yeah, okay, it's... Okay. Because I'm pretty sure it should be possible to do 128 U8s. Right? Like, why does this only go to 64? That's pretty unfortunate. I think it said, I think the instructions here were, yeah, maximum length of 100 bytes. Not 100 characters, 100 bytes. Is 64 really the max for SIMD here? That's really sad. What I was hoping to do was to parse the entire line using a single SIMD. Yeah, max is 512 bits, huh? No, but they have... So there's U16 times 64. So shouldn't there then also be U8 times 128? And I mean, to be clear, there are no lines that are actually that long in the generated thing. It's more that the spec says they can be. And we might have to do 2 SIMD instructions, which does make me a little bit sad, but so be it. Okay. So how does SIMD work? Well, so actually, let's start with what is SIMD. So SIMD stands for single instruction multiple data. The idea here is that you run one CPU instruction and it computes over multiple elements of data at the same time. So this usually means that inside of the CPU, there are sort of multiple compute units where you can give them, let's say, like 64 elements, and it can compute over all 64 elements in parallel with one instruction in the CPU, rather than doing it for element 1, then for element 2, then for element 3, and so on. And the way that you operate in SIMD mode, you get like the extreme version of SIMD is GPUs. We can do like concurrent, like in parallel. It basically has lots and lots of very small cores that can all do the same operation at the same time, but on different subsets of the data. And that's what we're looking for here, right? We really want to do an equality check with the semicolon for, are any of these bytes semicolon? And if so, tell me which one. And then SIMD has like you can do like a bitwise AND, for example, between 2 very long lists of elements. And you also have a reduce operation, and there are a couple of different reduce operations that take the result of one of those SIMD operations, like equality over 2 SIMD vectors, and gives you one result, like a U64, back from them. That, for example, could be a bit mask of which ones were equal. So here's what we're going to do. We're going to create a U8 by 64. So we want to call it a mask. It's not really a mask in SIMD terms, but okay, let's call it a, let's just say delimiter. The delimiter is a U8 times 64. And I forget what the constructor is for this. It's like, isn't there is it called spread? Scatter? There's like one where you can give one value and say that should be the value for all of them. But I think it just it also implements just like from, maybe it shows in the description. It does not. Okay. Resize? No, that's not what I want. Where's my constructor? Splat. Constructs a new SIMD vector with all elements set to the given value. That's what I'm after. So I want to splat a semicolon. So this will create a single thing of 64 U8s, all of which are set to semicolon. And I think what we'll do is if the line length is greater than 64, then we'll go to the slow path. It's going to be a to do. But otherwise, we'll take this SIMD one. We'll say that the delimiter is semicolon. And then what we want to do is get the current line also as one of these SIMD things. And then we want to do a concurrent, like a parallel equality between these two. So SIMD, where's my... Yeah, it's going to be unhappy about this because the line might be shorter, so we would have to pad it out. But I think there is a way to make one that pads, right? Load or default. Yeah, load or default is what I want. So I want a line is u8x64 load or default of line. And then I want to do delimiter, and then I want to do eq. No, I want to do .simd eq of line. Yeah. I want to use feature portable simd. Yes. Portable simd, please. Thank you. So what does this give me back? Well, this gives me back a mask. And what is a mask? Well, a mask is basically, we have 64 U8s here, we have 64 U8s here, and what we get back is a mask which tells us, which stores the result of doing that SIMD operations across all of these. And in fact, if we here go look at, where's my, so SIMD element is the trait we're after. You'll see mask here is for U8s, the mask type is an I8. So this is the result of doing operations over U8s is you get back I8s. So the I8 of doing element-wise equality is each equality is going to end up as an I8. And now what we want back from this is we want to know the offset at which the semicolon is. So how would we do that? Well, what you can do is look for what is it called? Is it zeros? Why can't I find the zeros? Yeah, so what I want is the number of leading zeros. But I think maybe I want to do a reduce first. No, I don't want to reduce. I want... Do I have AVX512? That's a good question. CPU... It's not CPU info. What's the test for AVX512? There is a command, right? Yeah, this one. AVX2, hooray! So I should get that. Dot first set maybe, yeah. So first set finds the index of the first set element in the mask, which is indeed what we're after, right? So we did the equality, and now we want to find the first one where the thing was set, and this is the index of the delimiter. Is this? This is now an option usize. It's option because it might never find the semicolon, but that shouldn't be the case, right? Because we're promised every line has a semicolon. And in fact, many of these expects could become, in fact, if we really want to go for it, right? We could do unwrap unchecked. Is there an expect unchecked? Because I want to write why, right? But here we could do safety. We're promised there is a in every line. We can always do the check later as well to see, if we use the safe version, how much would it cost us in terms of performance? So the index here is at what character is the semicolon, and now what we get out of this is, in fact, let's do that here. Let temperature and station and temperature are going to come out of this. And And so in the slow path, we're going to do this and give station temperature. And in the fast path, we're going to give back the index until the delimiter is going to be the station, right? So that's going to be line to the index of the delimiter. And the temperature is going to be the index of the delimiter plus 1 to the end of the string. Why is it mad at me? It's mad at me because I forgot to write line here. Oh. Let's do this way. Is there a reason I didn't use rsplit once? Yeah, there's no rsplit once on slices, or rather there is, but it's unstable. But I guess like we would need to pull in the library features slice split once because it hasn't been added yet. So I just made an rsplit n instead. But I guess in the interest now of we're using nightly anyway, so we might as well just do slice. It's just under split once. And then we'll do actually, we'll just do unwrap here. Which order does this return them in, though? It returns them in straight order. Okay, so this will be temperature and station. At which points, no, station then temperature. So this just reduces like that. Cool. And then maybe let's do, just to sanity check ourselves, line, station, and we'll do from utif 8. And because this is going to go away, I'll just use the safe version. Line, station, and temperature. That seems quite promising. Yeah, that looks real good. Okay, so now these print lines can go away. This branch, even though it is a branch, it's a branch we'll never take because we only take it for very long stations, which don't even happen in this data set. So this branch is an example of a branch that's basically free because the branch predictor is going to be perfect for it. Now let's see how much we ended up cutting. So let's do a guesstimate here. I believe this was about 5% of execution time. So we're at 28, so 5% is like, what, 1.4, so yeah, we're not going to save very much. We're going to save us a little over a second, right? Oh, not faster. Yeah, the print line isn't in there anymore. Try it a second time. We're already building with target CPU native. 29. Interesting. So this is slower. Why is it slower? Huh. All right, let's do a perf record. See what we get out of here. I also want to look at the actual assembly here. Perf report. What does perf tell us now? Nope, that's not what I wanted. I want to go into here. Main. Oh, I guess we should make this a function as well so that we get to know to station and temp U8 split semi, and it's going to give you back a U8 and a U8 just so we get that breakdown separately. Split semi of line. Oh yeah, this splat we only need to construct once. This is a const of n. Yeah, okay, great. So let's go ahead and do const semi u8 x64 is this. And then this should now be semi this. I mean, the splat should be pulled out by the compiler, I agree. So this feels like a red herring, but we can pull it out anyway. $27. All right, perf record. Actually, 27 is about right. Maybe it didn't hoist it. So we're at, right, we were at 28.5-ish, and we were expecting to save between 1 and 1.4 seconds. So that's about right. Nope, I need to kill this, right? I'm not waiting for this to finish. Perf report. Well, let's see what we get out of here. Is a split semi here is a very small amount of time, less than what we used to have. Oh, I guess the new line split is also not pulled out yet. So let's also split that out perhaps. So we'll do that line is next line, which is going to take map mutable reference to at, and that's all I think, right? It's going to take a U8, and here we do actually need lifetime annotations because we don't want this to be tied to the mutable reference of at, and it gives back a U8. Chord. Stop. Let's see what we get. Perf report dash G. Okay. What do we got down here? Okay, so next line of split semi now is a combined 5%. And it used to be a combined 10%. So not a huge amount of saving here. I'm guessing this is all memcar. Unclear we can do better than memcar. We could try to SIMD this as well, right? Because the new line should also be within the same. So maybe we do that. Let's save that for a little later. SIMD memcar. No, it's just SIMD in this one. All right, I'm pretty tempted to SIMD this one as well. There's also a fun thing where we might be able to SIMD the search for both of them at the same time. So the trick here, I think, would be... Oh, that's pretty tempting. That's pretty tempting. Here's what I'm thinking. You take the next 64 bytes. You subtract the value of new line. And now anything that's 0, anything that's 0 is your new line. And anything that's equal to the difference between new line and delimiter, which we can compute constantly, is the location of the semicolon. I wonder whether that's faster than doing each of these separately, but maybe it's the same. It would mean you only need to load the SIMD once. All right. I think we'll leave it like this for now, and then we'll come back later. Okay. So when we look at perf report, there's sort of an obvious elephant in the room, right? The obvious elephant in the room is, of course, max and min. No, I'm joking. Is, of course, the hash map. The hash map here is like taking almost all of the time. And even though there's only relatively few entries, like it's at most 10,000 different stations, this feels ridiculous. Like, surely we can do better. And especially because most of this time is going into hashing. And most of the time is hashing is using the default hasher from Rust, which tries to be like collision resistant and everything. So it injects like random data into the keying process as well. Like, this is stuff that matters for real Rust programs and is not cost we want to pay here. So there's a really interesting question of what do we want to do here? Because we can either switch this to like a B-tree map to avoid the hash, but now we're still doing equalities. But we're not doing Unicode, so it might actually be a decent amount faster. And B-tree maps are B-tree, like they allocate, I think, 5 elements per node. So you get some amortization here too. But let's first start with a sort of obvious improvement here, right? Which is with capacity 10,000. So remember what we had previously here was what, 27? I don't think this will make a huge difference. I'd be very surprised because we're only growing the hash map. I guess initially we're growing it quite a lot, but like amortize this will, like over 1 billion rows, I don't think this matters. But I could be wrong. I could be wrong. Ah, 25. Okay. Okay. So pre-allocation helps. Pre-allocate map. It's not quite pre-allocate, but you know what I mean. But I'm curious if we instead say that we make this a B-tree map. I just want to see. I just want to see what we get out of it. That also means, actually this we still need, even though it's kind of stupid. Because you should be able to compare these very quickly now that the keys are U8s, or byte slices, right? Because you don't need to do the expensive UTF-8 character comparison. So we're competing against 25. Oh, UTF-8 comparison is also memcomp. Okay, so then this should probably still then be slower. Okay, that's a lot slower. Cool. All right, back to hash map it is. Okay, let's also make this change. So we were talking about a little while ago. No, we decided not to do that because we might keep the pages around. Yeah, I want to optimize the mapping here before we start playing around with making these pointers. So the obvious next thing then is the hashing algorithm. So currently the hashing algorithm we're using is like the SIP hasher that comes in the standard library, which has like randomization in it and stuff. We want to avoid that. And so there are a couple of ways we could do this. We could bring in a crate like fx hash or a hash, but again, no external dependencies is the rule. We could have our own. So there are like Mersenne twisters, or not Mersenne twisters, but like we could just implement a hasher ourselves. There's also the stupid hasher, which is just like add all the bytes together. And let's just see. Like let's just see. Okay. I want a hasher. Dumb hasher. Sorry, I mean fast hasher. And this is going to be a fast hasher in there. Why is this being sad now? Why is it being sad? It's being sad because this needs to be this. Great. Okay, so fast hasher needs to implement build hasher, which creates a hasher, which is fast hasher, which returns a fast hasher. Fine. U64. Fast hasher, builder. Builder here because every time you need to hash something, you need to make one of these. So you need a builder that you can call to get a hasher. And this is then going to be 0 because we don't care about random here. And then we want to implement... We don't care about dealing with malicious hash collisions and stuff here. So we're going to implement hasher for fast hasher. Yes, yes. Yes, yes. Self.0 for b in bytes. Self.0 plus equals bytes. Actually, U32. And we actually want this to be wrapping add. Yeah. All right, self.0 is this. So this is a very stupid hasher that just adds the bytes of all of its inputs, and that's the hash. And we could even do this with like a SIMD add, but I think we might not need to. I wonder actually, is there a, yeah, right? Because we know that the hasher here is the station names, which are indeed just U8 bytes. We do, however, know that they are at most 100 characters. So we could SIMD here. So to do SIMD if less than 60, if less than or equal to 64b. Yeah, we could do a reduce sum here. But let's just see what happens. No, the SIMD here would be to do the addition. If the hasher now is just the addition of the bytes, you could do the addition of the bytes as SIMD. Now, this is obviously stupid, right? Like, this is not usually how you would mix in the hash, because it's much more likely you get collisions. And in fact, yeah, you see, we do worse, right? We were at 25 and now we're at 35. And I think it's because we end up with way more collisions. Because remember, you take this number and then you, like the implementation of the hash map takes that modulo the number of buckets. And so really what we want is to generate numbers that spread a lot. But what we're actually doing is just adding numbers where many of them are roughly the same length and many of them are ASCII. So you don't spread the value quite as well. So this is why you often want to do this using what someone proposed in here, U64 times U64 multiply, and then XOR the two 64-bit halves together. Okay, so we would, let's try that. Why not? So U28, and we'll do self.0. Is there a split? Is there a... I guess it's just this. Yeah, that's U64 modulo with this as U64. And then we do here. Chunks of sites 8. Actually, is there a yeah, that's what I want. Mute chunks is this of size 8. And then I want, because 8 is 64 here. So we do, actually, no, we can just keep a U64. We don't need to keep a 128. So this becomes self.0. And in here we do for chunk in, no, we do while let sum chunk is chunks because we need the remainder at the end. And then we do self.0 as U128 multiply by chunk, which here is going to be U64 from native endian bytes of chunk. As you would rate. Mixed, and then we'll do here. Mixed this, self.0 is equal to that. And then for the remainder, I guess we will just do the same, but there'll be U8, so we can't easily turn them into a U16. Well, I guess we could, but oh, right. And you need this can't be 0. This can be, there is some optimal number, like this should start with a prime or something, right? It should be co-prime with most of the numbers you might select or something. Let's just do 7. Why is it upset about this? Oh, right, next. And then for byte in chunks.remainder. I suppose we could just wrapping add these. Just pick a randomly selected 64-bit string. Where? Oh, for here. Yeah. Doesn't 7 is random, right? Nothing not random about 7. F and V's offset bias. Perfect. Thank you. Why not? And then I think, yeah, I thought about 1337. But hey, let's use a value someone chose. Chosen with a fair random roll die once. Yes, exactly. And then, why is it unhappy about this? Oh, why doesn't chunk exacts? Yeah, as chunks. That's what I want. Yeah. That's what I want. I want chunks and remainder. Now we're talking. And then I want to do for chunk in chunks, because now chunk here is an array. If it was future, I don't care about future. It's an array of fixed length. So now we can actually do this. Yeah, that's fine. Okay. What did I do? Why is it upset with me? This needs to be this. And then for B in remainder, what do I want to do with the remainder? I guess I can just add them in. That seems fine. Should probably do better, but oh, it needs, yeah, it needs to be a const. And then we can just add them in. We could mix in the same way, I suppose, but that feels excessive for the remainder here. Let's see. So remember, 25 is what we're trying to beat. 25 is the default Rust hasher. There's an interesting question here whether should this even be a hash map, right? Because we know there are at most 10,000 stations. And so we could just store it as a vector, although you do log n comparisons. That's not ideal. So this is slower. Interesting. Interesting. Yeah, I think I want to SIMD this. And I think the way, although that gets harder because now if we're trying to do it this way, then that's more painful because I'm curious where that time is going. Yeah, it's almost like the default one almost certainly has like a bunch of optimizations for vectorization and such, right? So that is what we're competing with. Why is it being sad about this now? That's confusing me. What? Why is it lost? Why it lost one of the stack frames in between, so it's like splitting these, which is sad. Equivalent key. It could also be that we're producing a bunch more collisions. Like, it's not necessarily that it's the hashing. Like, if I annotate this, oh, it's been inline, so I can't. How about we say inline never here? There we go. Now the stack trace is fine again. Why? Very strange. Yeah, so 80% is going there, which is roughly what it was before. Less time is going to the hasher. So that makes me think that this is actually more collisions. So what is happening to our hash here? Right length prefix. Oh, right. It also hashes the length of the slice. That's interesting. So I wonder if we could get away with just emitting 0 as the hash and just using the length. But let's see what happens if we annotate this, right? So where is this time going? Okay, function prelude. And it loads the bytes. It jumps. Why? Oh, this is the loop unrolling. Interesting. I'm trying to figure out. Oh yeah, it's vectorizing here. Interesting. Let's remove the source code here for a second. I'm curious. Actually, there's one thing I want to test. I think someone suggested it too. Like, what happens if we add like a hash here, for example. And then we try to use a hash, a hasher. What? A hash. What's their builder? Random state. I don't want random state. I want... I don't actually care that it's random, but I guess it's fine because the randomness is created when you create the build hasher. And I just want to see whether this is like where are we doing something stupid here? $16 seconds. Okay, so we are definitely doing something stupid. But is it collisions or is it the hashing speed? We should be able to test this pretty easily, right? Because if we here say get rid of the remainder, like how does that go? I'm just trying to narrow down where that time is going. So we were at 25, we got to 16. And then with this implementation, what do we get? This is definitely more than 16 seconds. It's not going brrr the way it's supposed to according to the name. $52. Okay, what if I just do bytes 0? Like just hear me out here, you know? It has to be collisions then, right? Oh, I gotta remove my inline never. Lots of arrays of length less than 8. That could certainly be the case, right? Like looking at the output from the stations list, there are a bunch of them that are less than 8, and those would end up with just doing remainder. And I guess the remainder we could do with SIMD here also, right? So we could just add those with SIMD. But my worry is that if we just add them, then we increase the number of collisions again. If collisions are indeed the problem. I guess we'll see what comes out here, right? If this is still slow, then clearly the problem is collisions because we're basically computing nothing now in the actual hasher. And it's only 8 bytes. which is the other thing that's interesting here. And like we could do a lot more than that. It's sort of, I guess we're making the trade-off here, right? Between, we could use like a U8X64. Arguably we could use more than that, but we're expecting these to be short strings anyway. So U8X64 is going to capture every station name. And we can just add them. The problem is then we're not getting the collision resistance because we're just adding them, and that's how you end up with the collisions in the first place. 112. Okay, yeah, so collisions here are very expensive. So it sounds like do more work to avoid collisions is probably worth it. So if we do something like a U8 over 8, so this will also be an 8 chunk, and then we'll do last dot copy from slice of remainder, and then we'll do chunks chain, I guess iter chain last, and this is actually, I guess this becomes remainder, but that's fine. Right, iter once of last. Shouldn't we use vec instead of hash map? I don't think so, because if you use a vec instead, you're gonna have to do log n string comparisons. So you're gonna do like somewhere around 6 string comparisons. Although I guess it's at most 10,000 stations, right? It could be way fewer. In fact, I think in the default dataset there are way fewer. And so then a vector would actually probably be pretty fast. Yeah, I think this will still be faster. Source right, I can't, it won't let me do that. Isn't there a copy? I think I can do mute last, make it a slice. What? There's definitely a way to do this. I'm so confused. Isn't there... If you copy from slice into a slice, the length of the source must be the same as self. There's a... I mean, okay, we can do remainder.len. It just makes me sad. Like this, that feels unnecessary. There, I'm pretty sure there is a, you know, copy as many as you can. Alternatively, is there a array, or is there a remainder.to array? All right, fine. We'll keep it like that. And this is like if remainder is empty, No, you're allowed to slice to 0, I think. If you have 0, then the hash becomes 0. Oh yeah, that's true. That's a very good observation. But we could just do this, right? Just as long as it's not 0, it's fine. Unless we like accidentally. You could imagine it accidentally becomes 0. Right? With the XORs. 21. Okay, that's better than 25, worse than 16. All right. Copy from remainder as pointer to last as mute pointer for remainder len. But that should be what copy from slice turns into, right? Make it branchless. Yeah. Where's the branch? The branch, I guess, is only really the termination case for the loop. Which I think you need anyway, because the byte input here is a slice of unknown length. Yeah, so this is still 21. So that didn't really save us anything. Which, like, I would be surprised if it did. Okay, well, 21 isn't bad. It could be that the mixing here is suboptimal, where like rather than multiplying this together, that we should add this multiplied by some constant. There's another thing we can do here, right? Which is just like throw more memory at the problem. Like if we have twice the number of buckets, we should also have fewer collisions. 21 is what we already had. I mean, it was slightly better. I still wonder if we could just SIMD this. Let's try. I just want to see. Oh, but then we get back to the collisions, right? But I kind of just want to see if I go ahead and do this. Right, so we go back up here. We say that the hasher is going to be if bytes len is greater than 64, then we're going to do the current stuff, right? But otherwise, we're just going to do yeah, this ends up being pretty weird, but bear with me. What if this is a U8 X64? I know, but hear me out. And this is 0. I know, hear me out. This is a reduce. No, because that would make it a U8, which it doesn't need to be. Product. This is going to be a what? No. Some, probably. What? Yeah, okay, that great. So that turns a U8, which is not what we want. So we're gonna have to do something here, but like bear with me. And then in this case, we do a we do self.0 simd add simd sum. Oh yeah, true. We could just do as u64x8, right? Which is the same type, or same size rather, and then reduce product, or reduce sum, or reduce product. Sure, why not? Why does it not let me do that? No, it's not a primitive type. Yeah, it has to be dot cast. U64.8 is not a SIMD type. Why? Lies. Lies, 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 lies. Oh, this only wants this. Okay, cool. But here we do a sum across the load of bytes. We don't need to do this. And we just say self.0 is this. Is it not SIMD sum? No, we're optimizing for less than 64. Right? So U8x64. So I'm trying to concurrently add all of them together. You see what I'm going for, right? Like I want to... Can I maybe just add them? Cool. This is just to do for now. Now, this is going to be worse mixing. This will be a U splat. And in fact, sure, this will be a const U8x64. Nope. U8x64 splat of 42. Why not? Doesn't really matter. And this plus equals this. Now, what I want to understand here is this will obviously be faster to compute. It does take into account all of the bytes, but it will have more collisions because we're not doing quite as thorough mixing. You think reduced product is worse here? I guess we'll find out. This is not 64 bits, it's 64 bytes. 64 bits would only be 8 characters. Yeah, this is definitely worse. This is certainly more than 20 seconds. Oh, you're right. You're totally right. It can't be reduced product because if any of them are 0, the result is 0. To be clear, I don't think our goal should be to build the fastest hash function ever built, right? Our goal should just be to make it close enough to what we know is achievable with AHash. And we can try the vector here as well. 40 seconds. So it really is the collisions. Because this compute should be real fast. So I genuinely then think that this old version we had, this version we had does decent mixing because we got to 21. What if we just like, I mean, I know birthday paradox and everything, right? But yeah, we could also, in that SIMD loop, we could have started the number differently from every character so that you take the position of the character into account. All right. A 4-byte chunk case instead of 8. Like this. And then this is a U32. I'm tempted to leave this one for now because I think we can drive ourselves crazy trying to come up with a better hashing algorithm here. Although I suppose Yeah, a lot of our strings are... A lot of our strings are like 6 characters. So they would end up in the remainder. But that would just be a copy and then it would be a chunk. Yeah. Okay. Let's then... This goes away. And we'll say this is good enough for now. It's so tempting to do this with SIMD. All right, I'm going to leave the hashing for now, otherwise we will spend literally all of the time on it. Where are we at here? So, hasher. Okay, someone said, please, please, please do the vector instead of the hash map. So let's try that. So we're going to make this be a vector of these guys. We're going to say with capacity is now going to go back to 10,000. We're going to do... We're going to do a binary search by key. And we want to search for station where the extraction is this. And if we get back an I, then this is stats I. Otherwise, we do stats dot insert at I, and then I think maybe this becomes a... It could be this becomes a DQ, but let's leave it as a vec for now. So insert at I. Station dot to vec. There I. And then stats is at mute stats. In fact, we could do get unchecked mute of I. Bah. Why is it unhappy? Station. Oh, this has to be. Yes, here's a vec of U8, yes. Oh, this needs to take like a reference to the key type or something. Okay, cool. This does nothing. So this is if let air I is equal to this. To simplify it slightly, oh no, we do need the I out actually. We need let I is is I, and this is also I. And then right, well, stats is mute, stats.1. Let's see. So now we're trying to skip the hashing altogether. We're trying to use a vector instead. And it'll be a sorted vector of keys. And then we do a binary search over that vector for the stations. My guess is that this will work pretty well if there are a few stations, but with many stations, it will be significantly slower. Yeah, this is definitely slower. Remember, we're trying to beat 21. This is way slower. Yeah. Rough. All right, back to hash map. But hey, we tried. Okay. To do this makes too many collisions. Yeah. Okay, what do we have next? Let's go ahead and do a perf record. And then we'll do perf report to see what we get. Nope. Ooh. Why? Okay. Fine. Why is all the time going in here? Did I leave an inline in here somewhere? No. Did I not let it run long enough? Yeah, I think I didn't let it run long enough. Let's see what we get here. It's all in the get mute of the hash map. Like all the other things aren't even registering. Huh. Okay, let's think. What can we do that's smarter here? So we use a try, but a try feels wrong here. Plus you need to keep track of you need to traverse a tree that goes to like depth of the length of the strings. I know parallelism is sort of the path to go down here eventually, but I'm just trying to think. Like this feels, because again, remember that the ultimate thing we're comparing against, right, is this, which, oh, why is that so slow now? Okay, yeah, which is 800 millis, right? That's what we're comparing against. So why is this one so slow? Well, let's see. If you go to source test, no, source main Java dev. Oh boy. Where is it? just tell me where it is. Okay, it's in source. Oh, main Java dev Morling calculate this. Okay, this was the like basically winning entry. Like, let's see what they do. Okay. Magic multiplier. Love that. The unsafe. Okay, so obviously they run in parallel. Let's ignore the parallelism here. They also do a memory map. That makes sense. This is all for splitting the map. For parallelism, we'll get to that later. Text builder, that's for the printing. Aggregates. So they allocate memory. Okay, so I think they have a find. What's this? Okay, they have two longs. Oh, I wonder if they do. All right, let me find their. That's for merging. That's the builder. No, I think this is just where they keep the stats. Because they also use a tree map from string to aggregate. Yeah, look, they pack the aggregates. That's fine. That's just how they combine the aggregates. What I want is their lookup. Aggregator. Okay, run. Here we go. So they get a segment. This is within one thread. They do a chunk. Okay, they split the chunk that each thread gets in 3. Okay, why? And as long as that's the case, why are they doing these? Interesting. So this is probably for CPU parallelism. And so they're trying to keep the... They're trying to keep the CPU busy enough by... I guess I think what they're doing here is they're relying on the fact that one CPU can have multiple outstanding memory loads at the same time. And so you want to make the CPU start all 3 loads. It's not usually necessarily 3, but like you want it to start multiple memory loads, and then you want to do the compute for all those 3 memory loads. Otherwise, you're just doing, in the CPU, you're doing one memory load and then doing the compute, and then one memory load and doing the compute. Right? So I think that's why they're doing this. What's this word thing? Word. That's relatively unhelpful as a word. Takes an address and gets the long at that address. Okay, so they read a U64 for the first 8 bytes of the name. Then they read a U64 for the next 8 bytes of the name. So they read the first 16 characters of every station name. What does separator do? Separator. So they XOR with the comma pattern. I think comma pattern here is just, yeah, 3B I think is comma. So they XOR the whole thing with comma bytes. So they're doing it in, right, and this lets them do it in a single register rather than with SIMD. And so you're scanning 8 you're scanning 8 characters at a time for comma. And you subtract 1 from each of them and you AND with 80. This has to be related then to the binary value of each character. Oh. Yeah, this is SIMD in a register. But did they do that on purpose or because they didn't have SIMD is an interesting question. Okay, so but what does this give you back? It just gives you the mask, I guess. Yeah, and then they look for the number of trailing zeros. Okay, so we'll go back to here. So this gives them the mask out of the, and remember this is, so word 1 and word 4 are the first 8 bytes and the second 8 bytes of the first chunk of what this file is looking at. Word 2 and 5 are the same for chunk 2, and 3 and 6 are the same for number 3. Okay. And then they run find with aggregates, chunk 1, word 1, yeah, word 1, word 4, separator 1, separator 4. So, yeah, so, okay, so interesting. This is also something we could do, right? We could totally do this kind of unrolling of trying to get the CPU, keep the CPU memory loads more active by doing all of the loads and then all of the computes. That's a really interesting insight. Okay, let's now look at the find. So what is their implementation of find? This feels like it's the main magic, right? Small. This is their fast path check. So if the separator is in the first 16 bytes is what they're looking for here, because separator 1 is a bit mask of, oh, that's totally what they're doing with the masking. The masking is trying to turn so they do an XOR and they want to turn they want to set everything to 0 except the first bit of the matching of the XOR. So what you end up with is a separator where you have zeros all the way until where the separator is. If these are both 0, it means the delimiter isn't there in the first 16 bytes. This also feels like SIMD kind of takes care of this for you. Yeah, and so if it's not small, then they do... Then they skip 16 bytes. And then they do something here. Let's look at the fast path. Length here counts... Length here counts the number of leading zeros. Pretty sure we saw that earlier. And then they mask. Right, and they need to mask here with the separators so that yeah, so that you only keep the parts of that word that aren't after the separator. Interesting. What's word mask here? Interesting. Yeah, so they are, depending on where whether the separator is in the first word, they decide whether to keep things from word 2 or not. So that's why if you look at the word mask, let's see, 0, 1, 2, 3, 4, 5, 6, 7. Yeah, so these are 8 entries. So if the length of separator, yeah, so this means if the separator is in word 1, then you're using one of these indices, which means your mask is 0. Otherwise, your mask is this. And if your mask is 0, it means you're turning all the characters in the second word, so the second set of 8 bytes, you're turning all of them into null bytes so that you're ignoring them. Otherwise, you do -1, which is all ones, so you're ANDing with all ones, which means you end up with the same bit pattern you had. That's clever. And then their hash is just XORing the first 8 bytes with the second 8 bytes. Yeah. I'm curious what their mixing function is. That's funny. Yep, it's a manual hash map. So they XOR the first 8 bytes with the second 8 bytes. They multiply it by a relatively random number. Then they XOR it with itself bit shifted right by 35. And then they return that value. That's great. Yeah, this does smell a lot like they're really trying hard to avoid branches. Right? Because they don't want to branch on things like, you know, is it less than 8 characters? Is it less than 16 characters? And so on. Interesting. And it does make, like, 35 as a bit shift here feels like hyper optimized, right? And look at the way they parse the value as well. They get the digits out. I'll go back here. So actually, we also need to look at aggregates.find. Find is just the... What? I think they just assume that the... Okay, so every bucket starts with the first 16 bytes, or includes the 16 bytes, and they conclude that the find is successful if the first 16 bytes match. So they're assuming here that the first 16 bytes are always unique. That feels sneaky. I don't know that I like that. Oh, wait, no. If the pointer is not equal to 0, then the return pointer. Otherwise... No, they don't handle collisions. They just straight up don't handle collisions. Because the find here just takes the pointer to the buckets, adds an offset from the hash, and it does check that the words are the same. But if they're not, it returns 0. And this can be the case for one of two reasons. One of them is the word isn't in the map yet. The other is you had a hash collision, and they don't distinguish between the two. Yeah, and the reason they kind of get away with this, right, is because... oh, what's it called? What's the name of the generator? Create measurements.java. Yep. So there's a fixed set of cities. And so all you need is a hash function that guarantees that these all get distinct hashes. So you do perfect hashing. That feels like cheating. I'm not willing to do. I don't think it's against the rules. Because there was nothing like... Okay, so there's two parts to this, right? One of them is if you're slower, if it doesn't match, if the hashes aren't perfect. That I feel like would be okay. But this is just incorrect if the hashes aren't okay. Yeah, I don't like that. I don't like that. I don't like that at all. Okay, so that answers our hashing question. Now, okay, so we could use the same hash function, actually. So it's funny because for us it's not cheating, because if it conflicts, then we still have conflict handling. So, all right. Mix. Where's our mix? Nope. So interesting. I wonder, is there a... We still have this right length prefix that I kind of want to... Like, why does that get called? I think I just want to have that be a no-op. And then here... So how do they avoid this being branched? They avoid this being branched because they just do reads into uninitialized memory. Right? That must be the case, because imagine you're at the last row and you read 16 bytes. If the last row has a station with like only 3, like 4 letters in the name or something, right? The worst it is there were 4 letter names. Plus semicolon plus, in theory, just 3 digits, 0.00, 0.0, plus a new line. That's way less than 16. As if you kept reading, you would read past the end of the memory map, which is unallocated memory, which is not okay. So how do they avoid this problem? Does Java just allow out of bounds reads? Well, okay, there's a variant of this, right? Remember, we found that the cost of write isn't really the problem. So how about we do this? We say this. We say if we don't even need to check. We can just say what do? They mix the first, they XOR they XOR the first 8 bytes. So how do I want to do this? I'm just trying to figure out if we can also make it not have branches. One of the rules is not to rely on specifics of the input, so I don't think this is okay. That's what this does. I don't know what to tell you. Maybe they didn't read the code, right? But that certainly feels skeptical. The problem here is, how do we branch when bytes could be less than 16? I can't map this as more memory because this is a memory mapped file, so I don't control what comes at the end of the memory map, and I don't control the input file. And this is called enough that branch misprediction here would be sad. But let's maybe just do 16 and say, all right, maybe this is how we branch. We say if bytes.len is longer than 16, then do this. Otherwise, do last bytes.len, copy from slice bytes with zeros, and then let left is U64 from any bytes And then I guess I can, do I have to do it this way? That feels wrong, right? Surely there's a, and so on, right? And right would be the same, but starting at 8, 9, 10, 11. And then let H is left XOR right multiply by this. But they're long, so they're I64s. Yeah, that's fine, that's fine, that's fine. Nope. I messed up my Vim. I messed up my Vimfoo. This should say 3. This should say 3. Then I can go here. I can do this. And then I can do 4 Control A. What? Why doesn't that add all of them? Oh, well, fine. I'll do it the manual way. Oh boy. Okay, fine. 8, 9, 10, 11, 12, 13, 14, and 15. Self.0 is H. As U64. Okay. Yeah, and this is not doing anything. Oh, I'm not allowed to do that. Fine. You can use try into. Yeah, but I shouldn't need try into here because I know the length. Let's see. At this point, why even do the hashing? Just copy the city array. No, there's a distinction, right? Like the goal here is that this still works even if there are collisions. The difference here is this just gives us a hashing function that happens to be good, right? So but unlike the original, if there are collisions, then we will handle them correctly. Although, funnily enough, this is slower than what we had. Oh, I bet you this is slower because of the copying we're doing. But this also suggests to me that, you know, part of where their win must come from is not just the perfect hashing, but also that their implementation can be a lot simpler because it can assume no collision, or because it ignores the collisions. So I actually think I want to go back to just this because it's correct and somewhat reasonable. Now, we had a conversation about maybe this should be let's maybe just just because it's fun, do this times just to keep the constant they gave us, you know. Do a plus here. Let's see. There's no comment about collisions in this file. Lies. Depends on the implementation you look at, probably, right? If this is also slower, that's funny, because that means we actually arrived at a pretty good hashing function. We're not doing too bad on collisions. So someone actually benchmarked the number of collisions, and ours is about the same. So there might be some other profiling. Yeah, okay. 27. So this is slower. I'm just going to keep what we had. And then some of the performance here is definitely going to come down to the map, right? They can just have a much simpler map than us, but they are still a lot faster. And we're spending all our time in the map. Ah. It's frustrating because it means there's not like not a trivial way for us to improve this, right? Because we could implement our own hash map from scratch that deals with collisions, but we're like unlikely to get it better than what hash brown can do. So it's like either you implement a map that like just doesn't deal with collisions, for example. You're storing a full vector keys and doing indirect key comparison. Ah, okay. So okay, here's this. Okay. That's true. That's true. Okay. Let me, what's our, okay, I'm gonna remove that comment. This is a very good observation. What if, let's, down here. So we're gonna have a struct, which is we're gonna call arrayvec, because that's basically what it is. And what it's gonna be is, it's actually even better than that, right? This is a stirvec. And what it's going to hold is a pointer. Bear with me here. And a length. Be a use size. And then I want the key here to be a stirvec. And now the trick with a stirvec is going to be that we're going to be really, really sneaky. Pubfn new. So it's going to take a slice of U8 which are the characters. I'm going to give you self. And what we want to do is inline shorter strings, because that way we avoid the pointer chasing to the heap all the time. Or it's not really the heap, it's to the mem map, but even so. No, it would be the heap because we're keeping vex. So if we store these inline, then we can pack into the pointer and the length what to do here. So here's what I'm imagining. I'm imagining that we're going to pack these such that if the len high bit is set, then even better, we can maybe use the alignment of the pointer. But let's say if the len high bit is set, then inlined into pointer then len. That's what I'm aiming for. Otherwise, pointer is a pointer to evacuate. I think maybe that way around. So if s.len is less than, how much can we fit in this? Well, actually, let's make this not a U size, right? This is a U64. A pointer is of, actually, they're both of U size. So let's assume here that we're on a 64-bit platform. Then we can keep 8 bytes in the pointer and 7 bytes in the length. We can't keep 8 bytes in the length because we need somewhere to store whether the string is inlined or not. And the reason I wanted this to be string vec instead of array vec is we know that there can't be null bytes in the string. Because that's also something that they said, that there were non-null Unicode bytes. And so as a result, we can do something kind of cool. If the length is less than 16, then branching here is a little bit sad, but I think it's going to be worth it. Most of our strings are going to be less than 16, so that part is easy. Then we want a self where the pointer is going to be this is where we need to be a little bit careful. I think we can do this branchless by saying the pointer is going to be 0 U8 of length 8. And then it's going to be copy from slice of S. And then length, similarly, is going to be 8, but I want length to be 2, right? Because the first byte we need to use for something special. In fact, we can pack an additional byte here, right? We can pack, yeah, so this can be 1, only the first byte is needed. 2, s.len minus 8. So this will be min of that in 8. We might need to branch here. based on whether we need to use the length or not. Right, so what I'm after here is just to demonstrate without it being correct yet. Is like s 8 length 0 is going to be 0xff, and then pointer here is going to be u64 from any bytes pointer, and then as usize as const u8. And len is going to be the same. I'm just trying to show what it is I'm going for here, right? So we're packing the characters from S directly into the pointer and length. Otherwise, we're going to say that the value is going to be is just going to be s2vec into boxed slice, and then we're going to say pointer is v dot as pointer self. Pointer is v as pointer, and length is v dot len. And as long as this length is less than like u64 with a high bit set, which it will be, this representation will be distinct from this one. As mute pointer, sure, why not? And this can also be mute, that's fine. And this can just stay a usize. And that's fine, this can be this. This won't actually work quite as written, but there's one other thing we're gonna have to do, which is if we're gonna use that as the key here, we're going to run into trouble here with getMute, because getMute expects that that we implement eq and hash, but also that we can borrow the key we give from the type that's in the map. Luckily, that's something we can do. So we can impl asref u8 slice for strvec, which is just if self dot length and so what are we after here? We're after 8 bytes, right? No, it's a u64, yeah. And really this should not be that either. It should be, why am I blanking on what the high bit is? 8? Oh, I did forget to leak the box. You're right. No, we don't have to leak the box, actually. We can implement drop here. Which is going to have a similar logic for restoring the box. Oh, you're right, but that does mean we have to do this. It's not leak, it's into raw of this. What? No, I want as mute pointer. Why is this unstable? Fine. Why? As mute u8. Unhappy about this. Okay, if the high bit is set on the length, then we know that it's one of these. Oh, we can't asref to u8, can we? Because they're not contiguous. So we actually need to pack even more. We need to have this be a length and pointer. All right, this is now it's going to be a union. Length and pointer, which is going to be a u8 of length 16. Inlined. Or it's going to be a heap, which is going to be a this and this. Wait, am I forgetting the syntax for union? Oh. Inlined is this. Heap is fine. Heap is this. Then it's a self. Actually, this kind of makes things easier because it means combined is of length 16. S.len cop. Actually, this is way easier. Combined. From 1. Copy from size S, and combine 0 is going to be all F's. That's fine. And then we will do strvec new. No. Self inlined. How do you construct the union type again? Oh, right. You construct it with struct syntax. Inlined is going to be combined. Otherwise, it's this with heap as pointer.len and this. Great. And so now we can do if self dot inlined 0. In fact, we can just say 0xf. We set it to ff anyway, right? So we can just check this And it's fine for this to be unsafe. Thank you very much. Because this is always set anyway. So if that's the case, then we know it's inlined. So then it is self.inlined, and this again is unsafe. It's not quite all of them though, because it's 1 onwards. Len is to do here. Right? Because we need to actually figure out, find first null byte. Otherwise, this is easy. Otherwise, we know we're in the other case. So we just do let pointer let len is unsafe self.heap.0 and pointer is self.heap.1 and this is std slice from raw parts, and this whole thing is really just unsafe. From raw parts of pointer and len. And then interestingly, drop is actually pretty easy because if this is not 0xff, only in that case do we care. And in that case, we can do here box from raw of pointer. And we can drop that. Sounds pretty easy. This feels like a... This one's actually easy, right? This is just... we could do this by just counting the trailing new lines. Sorry, the trailing zeros. No, trailing zeros won't work because you have you might have a character that ends with some 0 bits. So I think then this is just self.inlined fine. libc memcar of, I guess it's self.inlined. N here is 16. And we're looking for 0. And if end is null, then it's the whole slice. Otherwise, it is... Otherwise, the len is the end offset from... And then it's this. It's technically that -1, I think. I love the I think here. Unsafe. Don't do this at home, kids. Why is it unhappy? Oh, I guess technically this should be this. Actually, I guess this can just be as pointer C void. And get rid of my reference. And what's wrong here now? This is unhappy because that should be a void, which is not true. This should instead be a const u8. Should be the length, and this is fine to cast to a u size because we know that the end comes after the start. And this should be up to the length. Cool, and it's unhappy because it needs eq and hash. Now we can implement partial eq for stirvec. Super easy now, right? Which is just slice u8 as partial eq of self and other. And it's unhappy because we need to do this or this. How do I guess I can do as ref to make it explicit, at which point I don't even need this. I can do self as ref is equal to other as ref. And then I can also impl hash for stirvec. And similarly, hashing here is just self.asRef.hash of state. And then it's going to complain about something else, which is, oh, right, we also need eq. That's fine. Impl eq for stirvec. Is your system big endian? Otherwise, this will crash with strings of size 255. Why do I have my endianness inverted here somewhere? Oh, yeah, I do, don't I? Because the length here would be, yeah, if the length here is stored little endian, then the high bit of the length would be ff if length was 255. So okay, tempting then to do 2 big endian. And then to here do from big endian. Yeah, let's do that. Okay, so I have all the traits, and now it's complaining because it expected to find a reference to a stirvec, but get mute should be okay if the key implements borrow of q. So what we want is for the key type, in our case stirvec, to implement borrow of u8 for stirvec. And what we're promising by implementing borrow is basically the same as asref, but we're also promising that the implementation of hash and the implementation of eq are equal to that of the underlying key type. And so now getMute works. And so now this allows us to do lookups using slices, so we don't have to construct the stirvec. We only have to construct the stirvec in the case where we have to allocate. And now this can be this. This can be iter, so we can actually keep referring to these. This can be this. Watch this immediately blows up in my face, but I want to see what happens now if I go down here. Actually, I guess we'll see what happens. Build. Run. Trying to build 21 and we're trying to hope that it doesn't crash. Come on, be faster than 21 and don't crash. Faster than 21 and don't crash. I don't think it's faster than 21. The thinking here, right, is that we can inline the station string into the hash map, and that way the lookups should be faster. That's at least the hope. Now, this is slower, but why is it slower? Oh, it could just be because I haven't run it in a while. So it needs to be warmer in my cache. Maybe? But these names all look right. And this town names looks very like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So there are names that are longer than 16 and many of them are shorter. 26. Actually, let's leave that running a little longer. I want more representative samples. That's probably about good. Perf report. What do we get out of here? I mean, it's all in the hashing. So, but why? Oh, it's driving me nuts that I can't. Equivalent key, find, match tag. Yeah, I mean, basically none of this is spent in Sturvik. That's interesting. Like, it makes me really curious why this optimization is not better. We can do even better. Okay, here, let me just try one stupid thing. So we're gonna store the length in the first byte, because all that matters is that it's not 0. So we're gonna store the length plus 1. So that it's not 0 even if the length of the string is 0. And then this is just, if it's equal to 0, then it should be dropped. And this becomes, if it's equal to 0. No, if it's not equal to 0, then the length is is okay. I think I'm just gonna do this. Okay, this is just very unsafe. Just don't do this at home. Inlined. 0. Right? As usize. And now I don't need this branch. And I can just say that it's 1 to len. Minus 1. Yeah, it's all unsafe. I know. Will it go burr? What do we think? Will it go burr? I think it might go burr. Because that code was executed on every dereference. Although we are still... Yeah, because now it's just arithmetic over the pointers. 24. Okay, so we made it faster, but it's still slower than these being vectors. Why? Why? I mean... Okay. What if we're stupid? What if we just do that instead? That way we'll never miss the branch. Maybe. Because there are some... I mean, we could make it 100 even, right? Okay, so that didn't really make a difference. I was just thinking of like some of these places that have much longer names. Like this one. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. Shh, don't tell anyone. Everything is fine. It's all fine. Everything is, it's so good. It's all just fine. It's all good. Don't worry about it. Don't call the police. It's fine. I'm just really curious about why this is worse. Because the branch predictor should be perfect at that branch of whether it's inlined, because all of them should be inlined. 25. Hashing or equality should be the same as if it was just a slice, because they're just doing this. Oh, I bet you it's because the read isn't aligned anymore. That could totally be. Here's something interesting. What if we make it the last byte instead? So we say this. And then we say this. And then we say this. I just have a suspicion. Yeah, and this is actually, we don't even need the extra check here now because you don't need to offset. You think I'm leaking memory? Why? I think this should be fine. I just want to see, because now the slice comparisons are going to be aligned. And so that does make some CPU operations faster. Well, it's still correct, but not faster. Box from raw. That's true, but that shouldn't matter. The deallocation here should still be right. Doesn't know anything about the length of the allocation. I don't think that matters. Although, I mean, it could be that the deallocation just fails. I think it depends on when the allocator requires the length, but it usually doesn't. It usually just requires the pointer and to know the alignment of the pointer, which will be the same here. But I mean, it's fine, right? If you want us to, we can always do this. Can you even construct? Yeah, you can. Okay. So pointer len. No, it's like slice this guy I need. And then slice pointer. But I don't think that should matter. Yeah, all right. Const inline is a U8 is 32. Last is inline -1. I hope you're all happy now. But I'm still... So the reason I don't want to make this a bigger number is because you're bloating the size of the hash map. And if you bloat the size of the hash map, it means less of it fits in cache, which means you're more likely to miss in cache when accessing the hash map, which in turn means that your lookups will be worse. Because we're accessing the hash map a lot here. And so it's almost like I wonder if we should do less. Like the reason I wanted 16 here was because that way we're not actually bloating the hash map at all. If we do 24, then we are bloating the hash map because that's larger than the size of these two combined. And so you would end up with less hash map fitting in cache, which makes people sad. Can we do better here? I'm just, with 16, I don't quite understand why this is slower. Because it should strictly mean you need to do less pointer chasing, which means less stuff has to pollute your cache. Yes, 24. Feels a shame to throw it away because I'm like pretty sure this should be faster. Here's what I'm going to do. I'm going to do inline never on this guy. And then I'm going to do a perf record. I just want to see. I just want to see where this. Like, is there something we're doing that's real slow in there? And also, why do we still lose hash frames? I'm still confused about that part too. Sorry, no, why do we still lose stack frames? Chain. That's disturbing. This certainly makes it look like there are not that many collisions, because on collision is when you need to actually compare for equality, right? No, you always need to compare it for equality because you don't know if the lookup was a mix. But like, I don't even see calls to ASREF here. Collisions causing slowdowns and lookups. I mean, yeah. I'm just like, why? We might have to look at the performance counters here. Oh, this looks better. Still a bunch of time that goes into this, like, broken stack trace. Actually, here's what we're going to do. Get rid of this. Get rid of that. And then I'm going to do perf stat. I'll run that for a while. Okay, and then we're going to get diff. All that's here is the inlining, right? Nothing else. So I will get stash, and then I will cargo build, and then I will perf stat. I'll let it run for a while. I will kill it, and I will run it again, so we make sure it runs warm with the binary as well. And then I want to compare how we did here. So this is with the vec, and up here, I should really have, I should do this less stupidly, shouldn't I? Heap, not text. Oh, okay. Okay. Stash pop, cargo B. I'll just let this run for a while to warm up. And then we do this, but this will be inline. And then I want to diff, heap, and inline. So we have heap on the left, inline on the right. So inline has fewer stalled cycles, more instructions per cycle, fewer front-end cycles idle. So why is it slower? I don't understand. Branches. It has more branches and slightly more branch misses. It runs fewer cycles though, and it has fewer stalls. Has fewer L1 misses. Oh, it has way more TLB misses. Why? Specifically for the data cache. Oh, why? Why? This isn't any bigger than what we had before. right? Previously, the keys were vectors. Vectors hold a pointer, a capacity, and a length. So previously, it was even worse. It was 24 previously. Well, you're right. The numbers don't matter because I didn't run them for exactly the same duration of time. That's true. Although I was pretty close actually. Look, this one ran for 8.88 seconds and this one for 8.802. That's the difference between me running Control C for the two of them. So actually that was pretty good. And like 1.9 million and 3 million? I mean, okay, let's go over and look here. Yeah, like look here. DTLB loads. This is doing 2 million per second, and this is doing 320K per second. So this misses more, but this is doing way more TLB data loads. Why? Interesting. We shouldn't be polluting the data cache anymore. That's fascinating. We also have fewer branch misses, actually. We do slightly more branches, but we have fewer misses. Interesting. Okay, I have to think about that. I think we should take a quick break, and then I'll come back and continue. But I need to eat something and get some water. So we'll do a tea break, and then I'll be back shortly after. So I'll see you in like 5 minutes. And we're back. I now have water. I've eaten some amount of homemade pizza. I'm happy. Okay. I'm still trying to figure out what's going on here. What I noticed is that we also have more page faults. And I suspect this is related. Because like DTLB loads and misses are us trying to access, or the DTLB misses are us trying to access data that is no longer in the CPU's look-aside buffers. They're basically like, they've been paged out by the time we look at them. Now, why would this be happening is the other interesting question here. Like, why would we push things out of the TLB as a result of doing this? And I don't see why, because if you look at a Rust vec, right? The Rust vec source is at the very least a pointer and a length. And so if we're saying we're 16 bytes long, then we should be at most as big as a vector. So we shouldn't be polluting with any more data. We're also no longer accessing the heap in a bunch of cases. And so that should also be less pollution for the TLB in the first place. Maybe something SIMD changed. What if it's because of hash collisions? Well, this shouldn't cause any more hash collisions, though, is the thing. Yeah, we might have to just do some... I'm just like very... Oh. I should really have cargo ASM. Is this going to make a mess of my terminal? We shall find out. Whoa. What? What? Why is it doing that? Oh, I need to give it main. Main. Could not find function main. Oh, it's okay. Fine. Can I just do main? Can I not specify the hash here? Okay. I don't understand why cargo ASM is being unhelpful. Huh. Weird. The other thing is, like, do I need repr C on this? Well, that ran for longer. and it has fewer page faults per second, but it does still have the high number of data loads. You know, I wonder. It could be that I'm just trying to think whether vec could have an optimized partial eq or hash, as in more optimized than slice, but that feels unlikely. The other option would be if hash brown has an optimized implementation if the key is vec-u8. That also feels unlikely. The thing I'm really confused about is why are there more misses? Because we're not polluting, like we're not causing any more data to be accessed, like more distinct memory addresses to be accessed. So why, oh why, oh why? Let me just as a sanity check here, like the thing that changes is the size and bytes of the buckets inside the hash map. No, that does not change because I'm setting the size here to be the same size as a vec. Right? Like, well, okay, fine. A vec is 24 because it's length, capacity, and pointer. So, okay, fine, I'll make it 24, but we tried that too, and it didn't really make a difference. And so the bucket should be exactly the same size. Why? Yeah, still 25. Rep/c did nothing. And I mean, okay, just to check that I'm not. Yeah, it's 16. Okay, so we're not, it's not the representation that's messed up or something. Like, it is 16 long. Maybe it's sometimes tried to pre-read from the inline data, assuming it was a pointer. It could do that with vec. With vec, it could be pre-fetching. But like with the vec, it always has to go to the heap, which means it has to always access more data. Oh, you're saying it could, maybe it prefetches based on, it tries to prefetch this because there might be a pointer there, and then there isn't, and so therefore we prefetch stuff that's causing page faults or that there's nothing there. It seems unlikely. So there is this part, but like the -1 shouldn't matter. This slicing is also really just a subtraction of the length. I mean, okay, we're in unsafe land, right? So slice from raw parts, self inlined as pointer and len. But that, like, why would the sub slicing matter here, right? We could also add like an unlikely annotation on the path that loads, but the branch predictor should be okay, that was slightly faster. Just again, it's a sanity check, right? Like 21 is the thing we're competing with. What? This is 26 now? Weren't we at 21? We were at 21, right? I'm not insane. What? That's taking 26 now. So we are faster. What? I'm sure I saw 21 seconds when we were comparing to A hash. So this is faster, but that's unhelpful. Yeah, executed in 21 when we added the stuff for the hasher. What? Yeah, and then Yeah, and then next we tried the vector stuff. And when we tried the vector stuff, that was way slower. So that's 20 and 72. Oh, we do have more sys-time now. I don't know why we have more sys-time now. Well, okay, so what size was 100,000? I think I kept that, no? Yeah, I kept 100,000. Okay, well, fuck me, I guess. Well, this is faster. Great. This is just inline strings. And I'm fine with this being 24 to reduce the number of cache misses here. But let's, okay, so cargo B release. It's the room temperature. You could be right. Okay, so let's do this now. Let's do the CPU is tired, yeah. I just wanted to see comparing so this one up here is with 16 and this one down here is with 24. So with 16 we're at 10,000 page faults per second. With 24 we're at 12. 262 instructions per cycle, 262, 004 stalled. We have a lot of front-end cycles idle. And the branch prediction is slightly better with 16, but marginal. Why do we have so many front-end cycles idle? That means we're waiting a lot for memory to load. Okay, I want to try something. I want to try the same optimization that they made in the solution we looked at, which was to, in parallel, process each third of the file. Sorry, not in parallel, concurrently, because it's strictly not parallel, still one thread. So the way they do this is they take the file, they split it in 3. Okay, I think this is pretty easy, right? Because we can just do we have like at 1, at 2, and at 3. And we say map.len divided by 3, 2 times map.len divided by 3. And we need to be slightly careful here. Actually, I think what we really want to do is say slightly different. Map 1 is... So what are we going to do if we split in the middle of a line? I think what we want to do is to say you own reading all the lines that start after the position you're given. Or do we say you own every line starting from the one you're pointed at? I'm basically trying to figure out, like, if I'm pointed in the middle of a line, do I process that line, or does or is that line considered a part of the previous chunk? Which one's easier? It feels easier to say I'm going to look for my first new line and then process that. But that doesn't work for the first chunk. But maybe we just special case the first chunk here. Yeah, like, do I want to seek back? I guess the seek back is pretty cheap. So we would do, well, how would we do this? We would say, let at 3 is map until here. And then I want to... It feels real stupid for this to be iter r find, but iter var find might actually be fine here. And what I want to find is a new line. What? Can't compare. Okay. I thought you had that directly on a slice, no? Why don't we have find on this? Feels like it should be doable. But we could libc search here as well. But let's do it the stupid way first. So this will give me, I want our position actually. And then I want at 2 to be, actually, I guess these can both be like this. That's fine. So at 1 starts from 0. At 2 starts from this new line unwrap +1. And then we just need to make sure that they actually stop in time, which we do by saying that let map1 is going to be map until at 2. We say map2 is map from at 2 to at 3. And we say map 3 is at 3 and onwards. And then we say At 2 is 0, and at 3 is 0. And then it becomes line 1, line 2, line 3, map 1, map 2, map 3, at 1, at 2, at 3. And then it'll be interesting to see I guess. So the way they had it was if not line 1 empty and not line 2 is empty and not line 3 is empty, then they do this sort of joint thing. And then they did like if is empty. Line 2, line 3, line 3. Oh, why is it very unhappy? Found macro line. Did I? If line 1 is empty and line 2 is empty and line 3 is empty, then break. So if all of them are non-empty, then they did this. I still don't know that this will matter. Actually, I could maybe imagine it matters, actually, now that I think about it. Because it will mean that imagine the hash map has been pulled out of the TLB. Well, if we do all 3 hash map lookups back to back, then we'll pull it into the TLB once, and then we'll get to reuse it because the other axes are very proximal to the first. And I guess I can then do station 1 T1, station 2 T2, station 3 T3, just so I don't have to actually repeat these. I'm very curious whether this makes a difference. Doesn't feel like it has any right making a difference, but I don't even know what we're comparing to now. 23, 24, 25, somewhere around there. Oh, did I undo the 60? Yeah, I did. Okay. Yeah, this is for sure slower. it's very much slower, actually. Whoa. Yeah, that sure feels wrong. But but why? Oh, this is the probably index into map. Well, that is interesting. Yeah, I need the backtrace here. Yeah, all the ats should start at 0 because they all get a dedicated map that has the correct start index. But why did it crash after 40 seconds? That makes me feel like it crashes when it tries to print. Crashed at 237. 145. Map 3. Oh, I know it's broken. It's because of the end condition. It's because we haven't written next line such that it, like, if at is already at the end, past the end here. Yeah, it's this part. It's because yeah, we can fix this by doing this, and then we don't add 1 in this case. What? Oh, and this. But this still suggests that it's failing when it's trying to terminate the loop, which means it's already tried to run the whole thing. Which means total execution here will be somewhere around 40 seconds. Why? I mean, the hope here, right, was that we would... The hope is that we would... Yeah, 40 seconds, okay. Do we end up with the same results? Just sanity check here? I think so. Yeah, it looks the same. What were they doing in their preloading? Like, what does Word do here? Yeah. It just gets the value at that address. So they read the values at each of these addresses. Which should be pretty equivalent to what we're doing here. Right? Like what we're doing at the beginning of each of these is when we call next line. Or these are just constructing pointers. And then we call... we do start the search already. So this makes me wonder if... it makes me wonder whether we could do a sort of prefetch hint to the compiler here, or to the CPU, rather than do the memcur. The thing I'm worried about is that we end up stalling the CPU because there are too many instructions between the load and the next load. And so the way we could do this, I think, is one. Now this won't actually work, but we could maybe do hint black box to basically tell the compiler, hey, don't get rid of this access. I don't think that'll make a difference, but we could try. I wonder if the compiler isn't inlining those functions now. Oh, you could be right. You could be right. Let's let that run first, just to see. That could totally be, and that would have a similar problem of there'll be too much code in between the two. Advice sequential isn't correct anymore. I think it is, right? Because so as far as I understand, the point of advice sequential is that the kernel shouldn't keep a page around anymore just because it's been read. So the intent being that as you stop reading a page, the kernel is okay to get rid of it. So things will disappear more rapidly. Oh. Okay. Well, that means there is a load for them now. But let me try to see if I don't do that. The error, the reason here is because at can point at the end of the array, and so there's nothing to read. And the inlining might make a difference here. I think we really need to look at the assembly here for what it generates. I'm annoyed that cargo ASM doesn't work. Although we can look at the perf will give us roughly the same thing with some annotations. No, this is still definitely slower. Interesting. Interesting. What if we just did 2 instead of 3? Like why is 3 the right number here? So the reason this is supposed to help is because it allows the CPU, it allows us to make the CPU load 2 regions of memory that we're about to access at the same time, and therefore in parallel. So currently, like if you don't do this, right, then imagine one CPU core is running. It wants to load the next address, and then when that loads, then it will compute over that. But while it's doing that compute, in theory, it could be loading the next thing we're about to process. But currently that there's no I/O overlap here. Or actually, maybe the way to describe it is more, while it's loading, the CPU is able to load multiple things in parallel. And so currently we're only giving it the ability to load one thing at a time. With this way, we should be able to have the CPU load multiple things concurrently and therefore not be stalling at every loop. That was the thinking. Cargo ASM bin... Brr. Cargo ASM... There's no such thing. Do I have the wrong cargo ASM? That is the cargo ASM I have. I mean, there's also cargo show ASM, but now I'm curious. This was updated 5 days ago. This was updated 6 years ago. I have the wrong cargo ASM. Cargo uninstall, cargo ASM. Cargo install, cargo show ASM. That's why. Cargo ASM bim 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 brr. I want main. Can I get main? By name or by sequence number? Zero. Okay. What do we got here? Feels like more instructions should be needed. Also, I want comment annotations to know where I'm at. Why is there panic machinery here? Why is there panic machinery? Okay. Oh boy. This is all the hash table stuff. This is going to be less helpful than I'd hoped. I want Add dash dash everything. What does that do? I don't think that's better. We already have panic equals abort. I want to find no. I want to find next line. Why isn't it? This is not helpful. What? Yeah, I need something that's way more scoped here. Even if it got mangled, it should still have next line in the name. I just wanted to give me the assembly kind of starting here. All right, what do we got here? Cargo ASM help. Keep labels, keep blanks, reduce labels. Keep blank lines. Well, that's not super helpful. Include other called functions recursively up to count depth. This defaults to 0. Well, that is what I want, but it doesn't seem to be what it's doing. Rust, this workspace, C1. Like, this is clearly emitting things that are much deeper than 1 deep. I just want the assembly. Okay, we're going to not do that this way. We're going to instead do perf record, let it run, and then annotate main. Perf report. Annotate main, please. Advice, malloc, memset. Give me the source annotations, please. Okay. This is already where we're doing that. I want to find, that's the map entries. Wait, no, this is the This feels very jumbled. Next new line is null. This is the is empty call. Okay. So this seems promising. If line length is greater than 64, which is, it never is. So then we get down to the SIMD stuff, SIMD eq. Okay, so this is split semi. Right? Yeah. I'm wondering. Oh, wow. Perf seg faulted. Cool. Annotate this for me again, please. Line parse. Yeah, we're not executing that line at all. We're instead taking the SIMD here. And so that is taking some amount of the execution of main. What's confusing me is like, okay, this is percentage of the time spent in main. Oh, it's probably of the self cost of main though. Is there a way to add a column here for, yeah, T. No, that's not what I want. P. Yeah, so this is percentage of overall execution time. Yeah, so these add up to basically nothing. Is finding our... Oh, and then it seg faults again. Okay, cool. Annotate, switch to global, tab. In fact, none of these are particularly hot, which makes sense because all the time is spent in the hash map lookup. Interesting. So I don't think we can even like... It could be that this makes a difference, but it doesn't, like that we could make this make a difference. But given that all the time is going to the hash map, it just doesn't. Which is pretty frustrating. Flame graph wouldn't help us here. It would give the same as what we get from perf report, which would really just tell us all the time is going to the hash map. Okay, here's another maybe stupid idea. I am gonna keep this and re-entry. Not gonna keep this. So one other option here that we could explore is to have a hash map per first character. It might be stupid, but it might also not be stupid. Let me just. This should probably have way fewer. Right, this should have like 64. Car hasher. This will only ever hash characters. FN right. What is the implementation of hash for character? What does it call? U32. I suppose that makes sense. And so this is then just going to be U128 from right. And then we're just gonna sit. No, I did something stupid again. This is just gonna be a to do because we should always be hitting that one. I just kind of want to see. It can't be a linear array because the, well, I guess we could just do the first byte. Maybe we just do the first byte. Because these are Unicode characters, right? So the first byte could be the umlaut. But fine, well, we can do that. All right, I buy it. I buy it. All names are not ASCII. So we'll say that this is a, then this changes slightly. This becomes a array of these. Yeah, I think we're gonna, okay, let's try this. This of length 255. Well, I guess 256. And it's going to be std array from fn. Hash map. So we create one of these. We say stats is stats this could actually end up being worse because we'll pollute the TLB more, but this can probably now be 10,000. Why can't it be indexed by U8? Well, that's interesting. I don't understand why this needs to be... Shouldn't it be obvious that this is this? Why is the compiler unhappy? Oh, because this is a U8, but this is an array, so this needs to be usize from U8 is why. And then down here, we actually need to do stats.iter dot flatten why 256 and not 255? Because you can, if there are 256 possible values if you count 0, no? Am I being stupid? Yeah. Okay, so that's not faster. Even though this should reduce collisions. Yeah, we should be able to be way smaller than 10,000 here, right? We should be able to do, I mean, we don't actually know the distribution, but let's say we do 1,000. But even that, I don't think should make a difference. Yeah, the hashing here is just very upsetting. $26. Yeah, so it doesn't really make a difference. 390. Sure. I don't, even if I make this 300, right? I don't think this will be, I don't think that this will really help. Not to mention the keys aren't uniformly distributed over the first byte. My guess is it'll be about the same, maybe slightly worse, actually. It's slightly better. But overall, this is still worse, right? Like, if I get stash, I can't type. So we were at 24. I think this is like, I think this ends up being a wash. You know, maybe the problem is that we've made the hash map too big. Okay, so there's a slight win to this, but like, it's marginal. If it was a reasonable optimization, the hash map would probably implement something similar. It can't necessarily, right? Because it doesn't know the nature of the distribution of your inputs. Yeah, they're like about the same. But it does make me wonder. Like, what if we did this? Like, just reduce the size of the hash map without the without the pre-bucketing by the first byte. Like, does that buy us any time? Doesn't seem like it. It's about the same. I'm just thinking, because if there are fewer buckets, then yes, you collide more, but you also you use less of the cache, so you're more likely to hit in your cache than miss. I mean, what if we made it even smaller, right? Like, what if we made this 1,000? I just want to see if there's like a meaningful. Although I suppose we might just end up with a hash map resize. We won't necessarily know if it has an impact. Oh, that is faster. I mean, what happens if I just... how many unique stations are there in the input? Up to 10,000. But for this particular generation, I'm not sure. I mean, we could easily print it out, right? We have it above here. This many. So that's 1, 2, 3, 4, 5, 6, 7 times 10, 20, 30, 40, 50. It's about 500. Yeah, so that didn't really save any more. In fact, letting it dynamically size did the same as when we set it to 1,000. Which sort of suggests we could set it to 1,000 to save a couple of the initial resizes, but and I think this could go away. Okay. It does really bother me that we can't optimize the hash map out of this more. I mean, we could, right? Like, we could implement our own hash map here with a better default strategy. But what's the other one that was like, I think this was one of the other ones that did really well. I just want to see what they do for the map itself. That's just... You see, they do the same thing of having multiple concurrent scanners. And I think this is to basically do preloading. Although that didn't really matter for us. But it could be that it would matter if our hash map wasn't such a bottleneck. But what did they end up with here? They use record. What does record do? Final calculation for the index into the hash table. They compute the hash as the XOR of the first 8 bytes with the second 8 bytes, which is similar to what the other thing did. And then they do hash to index, which is just a bit shift by the number of buckets. Yeah, this also feels like hard coding, right? Like this just... Okay, check for collision. Because up here, they just look up existing result, and if they're equal, then it returns existing result. Okay, but what do they do on collisions? If they get a collision, yeah, then they probe for a different index. But they don't do that here. Like in the lookup, they don't look at any other hashes. Right? Am I being stupid? So here, they're extracting word 1 and word 2. They're computing the hash, fine. Then they turn the hash into an index, which is basically a bit shift to do a modulo. And then they look up in results, which is the table they have, like it's the bucket list. And if that entry isn't null, then they check that the name is the same, and then they return. If it's not, I see. If it's not, then they go here. So this is for insert and for lookup. I see. But presumably, this is what hash brown does as well. Yeah, I think the trick here is to basically do the same. All right, how about this? I think we need to bring out some heavier guns here. Not that we haven't brought out heavy guns so far. So we can either use the raw HashMap API to do this, or we could have our hasher just instead of all of this stuff, we just say that the hash is word1. I feel like we've already been down this path, but we will do it again. So damn me. Word1, word 2. Actually, no, just word is this, which is 16. And then word dot copy from slice bytes dot len. And then word is now we should be able to cast this into word as U64 2, right? That should be, I said we were going hard here. Transmute that, because these have the same memory layout. U8 16. And then we're going to do word 1 XOR word 2. Whoa. Why? Index 24 out of range for slice of length 16. Oh, dot min of 16. What? Source slice length does not match. I'm sure there's a version, there's like a memcopy thing that will copy at most the minimum of the 2 bytes. Pointer copy from bytes as pointer to word as mute pointer of length bytes.len.min 16. Yes. Now, part of what bothers me here is I'm pretty sure there's an extra call to our hashing, which is when you hash a slice in Rust, it will also include the length of the collection as part of the hashing. Right, and that's, I think, because of this extra thing. Like, if we now do perf record, U816 and U64.2 do not have the same alignment. That is true. I suppose I can bring out the big slogans. That's true. Because in theory, it could go the other way. Which I suppose is what we would have to do. I just want to see. Yeah, exactly. I want to see what on earth is going on in here. Now we're spending more time in splitting. Why? Yeah, we're spending almost no time in hashing now. We're spending way more time in equivalent key, borrow. In asref. Well, that's interesting. Is that because we have more collisions? Hashbound uses the top 7 bits of the hash to group buckets. So you need to use a hash function that gives you good entropy in the top bits. Yeah, unclear that we currently get that. What I'm trying to figure out is whether this is like linear probing that's causing us to do way more calls to borrow. Yeah, I think, all right, let's try the, okay, so we'll do this as 0.64.2, and then we'll copy, we'll do the transmute here. U64.2 to U816. In fact, this just goes from a star mute U64 to a star mute U8. That's the actual transmute, right? Because this function, I also want to be a no-op. Hasher prefix-free extras. And then someone was saying invert the bits. Or for pointers you can that's true. This can be a dot casts. U8. No, not bit mixing and finish at all. This is, now I'm just trying to copy the exact same hashing function that this solution is using. And it is just a straight XOR between the first 2 words plus oh, they are actually doing that. You're right. They're doing, oops. No, you're totally right. We should do the same. 0. Yep. Now, I don't think this is gonna... What I'm trying to decide here is whether the problem here is 22. Okay, I mean, that's a little faster. I'm just trying to decide where the time is coming from here, because this ends up being a little bit misleading. Because if you look at main here now, if you look inside of here, well, okay, we're now spending more time in this because of the mixing and finish. It's interesting though, we're spending 40% of our time in hash finish. Like genuinely 40% of our execution time is this. Like not even the internals of the hash map, just the computation of the hash. That seems wild. A third of execution in those 3 XORs with bit shifts. And then it's spending 50% of the time in get mute equivalent key, tag full, match tag. So match tag here is looking for the, this is like internals of hash brown, right? It's like deciding like grouping the buckets by the high bit of the hash, and then it's scanning all of those tags using SIMD stuff. But like, how is all the time going here? I just don't understand. What if, okay, just because I feel like I'm going nuts. It could be lying to us with sampling. We could do, whoa, what? No, stop whatever you're doing. I don't like this one bit. Okay, let's do -F, like 1,000. Oh, this sets the sampling frequency for the underlying process. So I'm making it wake up less often. also don't understand why a bunch of this is getting disconnected from start. I mean, they end up being the same. I'm just... Why? This calls... This is the only thing that's weird. Why? So we get hash 1, but we don't actually see, like, why is fast hasher here inlined? I said inline never. Oh, finish. Right, I also want right. And I may not have compiled in between. The multi-threaded Java version is using all my cores. I forget how many cores I have. Let's find out. I have 32 cores. So we'll get a significant speed up from the parallelism. I just, like, in a way, don't care about the parallelism because the parallelism is easy. This also doesn't make any sense. Why do I now see the other things take more time when slowing down the hash map by setting it to inline never? All right. What we got in here? Main. Make hash. Hash 1. Okay, 50% is spent in... Okay, so hash 1. Now 7% is in finish. What? Perf is definitely lying to me. 7% in has been is finish. 50%. Okay, so these add up to... Okay, yeah. So most of it is spent here. And hash should just be calling... Or hash 1 should just be calling hash and finish. So it calls hash, which calls hash slice, which calls our hasher right. And if we annotate this, that's the assembly for it. Interesting. So the XOR, we are now spending most of our time in the hashing. Not in things like the traversal of the hash map and stuff. And we're spending a third of the function, of specifically of the hashing function in the XOR, and 2/3. Now, this is probably misleading on the perf side of things. In the move. Why in the move? It's the write back into memory. Into self. I don't think we're going to get this hashing a whole lot faster. Like, okay, we can rotate right here, for example, right? And we can, this can be a rotate right. Someone suggested in chat, and that's all true, but like, I don't think we're going to get a whole lot more performance optimization out of here. And like, I think realistically, we're not getting rid of this hash map stuff. So we might want to go to parallelism next. Next line is mostly now memcur. And this one, I think we could just replace with a single SIMD, sort of similar to what we did here for split semi. And so that might be interesting to look at. Parse temperature also feels like we could probably make faster. You know, I think what was maybe throwing off our ability to figure out where the time was being spent was that we were inlining these, and therefore it just all got sort of wrapped up in the hash map code. I think let's keep it that way. And then let's see, what do I... So I think the comparison point here we have is like 24.5 seconds. Let's try real quick to make the next line thing use SIMD. But we can't necessarily. Yeah, okay. Oh, what? Now it's 21? What? Oh, I'm losing my mind here. 21 is what we had earlier. We've just changed the code back, like forward and then back again. You can experiment with different number of lanes pretty easily. Yeah, that's true. The CPU is cooler now. It could be. All right. Well, I don't even know what to say anymore. More efficient hashing. All right. Let's do next line. And do this. So if the So how do we want to do this? We do this by saying we have semi and we have new line. New line is a new line. And I think the fallback here is going to be like if we don't find a new line. So this is going to be... Elements are read so long as they're inbound. Okay. Otherwise, they're filled with defaults, so we can just pass rest here, actually, which is pretty nice. And then we will find the index of that new line, but we're not guaranteed that there is one, because it might be... because it might be that it might be that the delimiter is not in the first, but we can only search 64 bytes. So the search may have to fall back to memcar. So otherwise, we're going to do, it's not actually rest, it's rest. It's actually rest starting at 16, right? Because starting at 64, because we've already searched the first 64 with SIMD here. Minus 64. And so if this also says, no, this isn't necessarily safe either, because down here we could be in a, oh no, we know there's supposed to be a new line. We know there must be a new line. So rest 64 must be non-empty. So rest is rest from 64 and onwards. And this is now rest. If we still don't get a new line, this is not reentrant anymore now, but that's maybe okay. I actually think I want the place that calls next line to be the one to update at. Feels weird for it to be updated inside of here. So I think we're just going to say at. So if next new line is null, shouldn't be possible. Because there should always be a new line whenever you call next new line. And if that's not the case, the loop outside should have exited, which is unsafe, but fine. So this is now an offset from rest, right? Because that's what we passed in. And so we now want 64, plus that length is the, that is the, yeah. If this, then I, otherwise this. So this is now, I actually think maybe maybe this just returns next new line and it leaves it to the caller to figure out how to deal with that. So this is now so if, oh boy, I think we need to keep track of oh, maybe not. Maybe we just say let line is map from at to new at, and then we say at is, I guess this is really new line at, right? And then we say at is new line at plus 1. And new line at here is, what is that relative to, is the next question. Yeah, so this should really be at plus I. And this should be which really we can just say here that up here, oops, that new line at is going to be at plus this plus, that's where the new line is at. And then we want the line is from where we're at to where the new line is at. New at is where the new line is at plus 1. Yes? Yes. And if that line is empty, which would happen if no, that doesn't work either, because when we find the last new line in the file, there's still stuff left, but there won't be another new line. So I don't think we ever hit this unless the file ends in a double new line, which it does not. So I do think we actually need to here detect that if rest is empty. Yeah, okay. So this is just, we can just make this be while at is less than map.len. Let's see it run. I'm profiling my madness at this point. Yeah, you're not wrong. Double new line breaks the promise of no null station name. Yeah, but there's no double new line. 23. Okay, we're back up to 23 now for some reason. But okay, so it didn't get slower, but it also didn't get any faster. Interesting. So doing this new line search with SIMD compared to using memcar doesn't really make a difference. I do still feel like there should be a way to search for the new line and the semicolon at the same time. I also do wonder, like, do we ever get here? I don't think we do. Right? Yeah, okay, great. We never get there. So now we are just using the SIMD for the lookup, but we need to have the fallback. Which is fine. But it isn't faster. That's wild to me. All right, well, we SIMD'd it, why not? The parse temperature, I'm also pretty sure we could optimize. Like, this feels real dumb, right? Let's SIMD new line search. For parse temperature, what could we do here? Well, we could use SIMD to search for the full stop, but that seems unnecessary. I really want to avoid the branch here and the termination condition for the loop. So, okay, here's something stupid. We don't need to do the subtraction. We can just subtract after doing all the accumulation. There's no real reason to do this every time we parse, I think. But how do we get rid of the fork? Well, this... trying to think if there's a structure to the string here that we can make use of. We know exactly the structure of the last 3 digits always. We could swap the last 2 U8s. That's a good point. Only problem is we don't have... We don't have mutable access to it, but we could copy it out. And that would remove that branch. I like that. And I also think we could say T is... And we can actually swap the... Can we swap the sign to the end? No, because we're not guaranteed that it's there. But what we can almost certainly do here is we can say that this is 0U8 of length 5. right? It's at most 5 long. Right? Minus 99.9, most 5 long. And then we could read. Yeah, but if we do a copy from slice here, we kind of want it to be right aligned in order to know how to swap the last two. I don't think the subtracting 0 cost us all that much here. Like realistically, it's probably just going to run in parallel. So there is something interesting here where I have to look at the excuse me for a second, I need to look at the ASCII tables. Man, ASCII. Where is minus? Minus is before all the numbers. What about period? Period is after. Okay, so here's something interesting you could do. There's actually do numbers have copy sign? Oh, it doesn't. That's a shame. So on F64s, you have this thing called copy sign that lets you copy over the sign of another thing, which is branchless, which we don't have here. But so if we copy from slice, source, no, temperature.len. Then now we can do t of t.len minus 1 minus 2 is equal to t of t.len minus 1. So now we're removing no, we actually need to swap them, right? Which is not gonna let me because I can't have two mutable borrows at the same time. But there is a get disjoint mute where I can do t.len minus 1 and t.len minus 2. And then I can swap t1 and t2. Put dot at the end. Unwrap unchecked. These are for sure non-overlapping. Right, and this is t1 and t2. And now I can swap them. T-len is t.len. Now we swap them. Now we're eliminating that branch. And then for the minus, how do we do the minus? What I was thinking was to do T0 minus this. So this will be 0 if it's dash, and it will be, no, it'll be, what am I saying? This, I want to be an I8 actually. It's going to be unhappy with me. But there's no real reason why this couldn't be. I guess our M map here, it can just as well be I8. Right? There's nothing that says this can't be an I8. And an oh, but this is going to be a U8, huh? But like, a character is really kind of an I8. All right, fine. What I'm trying to get at here is, I guess I can just do as I8. Minus this, so now that will be 0, and any other number will not be 0. Sorry, any other value has to be a number, and all numbers are up here, right? They're higher than this. So we either get 0 or we get one of these numbers. And then I want to mask it. Actually, let's make that be dot instead. So now this will be -1 or some positive number. And then I want to mask it with, I want to mask out just the sign. Is there a way for me to get, what's the sign bit of an I8? Right? I want to mask out just the sign bit. Oh, returns a number representing the sign of self. Perfect. Yes, that is what I want. So this will now be -1 for minus and +1 for anything else. So this is now sign. And then now we can do this, and this should now iterate from 0. Can we make it not have to branch? We can get loop unrolling here by, yeah, we could skip sign, but if we skip sign, we're introducing a branch in the iteration. I'm trying to not do that. How could we do that? Let's look at the bit patterns here. So what even are numbers? 3. 1, 2. Okay, so that means it's 1 1 0 0. I'm just trying to see if we could do a bit mask here to get that out of the way. what I was thinking is there a way we can unconditionally walk all of the numbers and just add them together? And I think there might be. So my thinking was, what if we just also add in the dot and then just subtract it afterwards? But this doesn't really help because we still then need to check the length of the array. No, it does help because then we can always just do it for the first 3. And if we happen to include the dot, then we don't care. But we need to check whether we need to remove the dot or not. Which we can do by... Oh. Are you sure it's a branch and not a pointer increment? Well, but it would be a conditional pointer increment. Oh, I guess you can cast the bool to a 1 and use that to decide to skip. Yeah, it comes down to whether it comes down to whether if we do temperature, oops, what? Temperature dot iter dot skip if if t0 is equal to b dash, then 1 else 0, right? I'm not worried about branching internally in skip. I'm worried about this specifically being a branch, right? The sign is an integer, yes. But sign will be 1 or minus 1 is the problem here. Yeah, this should be a conditional move. I agree it should be. I think it's interesting whether it would be. Oh, sign 0 minus sign is interesting. That doesn't help us because that just flips the sign. Yeah, I agree. This should maybe then be fine. Okay, so then we'll do this. But now we still have an iterator that needs to check for termination. What I was hoping for is for us to do a... All right, let me see if I can express what I'm after. In fact, maybe this is the way to do it. I want... Here's what I want. I want t to be t skip plus 0 times no. If if t if tlen is is tlen minus skip is equal to Oh, this is hurting my brain far too much. Is equal to 4. Uh, then 100 else. No, it's actually 1,000, otherwise 100. I think you see where I'm going. And then I want T1 is mol times T skip plus 0 minus B0 2 and then mol divided by 10 skip plus 1 mol divided by 10 2 and now this T3 needs to be conditional because it could be that there are only 2 actual digits, in which case this is a dot. So I think this needs to be if if tlen minus skip is equal to equal to 3, then is equal to 4, then 1, else 0 times that. T is T1 plus T2 plus T3. Right? You see what I'm after? What's mol here? A mol here's... No, I need this to be an I16 from... This needs to be an I16 from... And this needs to be an I16 from. And then... this stupidly needs to be an I16, and then this will then be sine times that. Right? I now here's what I think we should do. Inline never this cargo B. Where did this what is this IFA thing? Go away. I don't want you. And now I want cargo asm. No, cargo asm. Bin brr, parse temperature. All right, what do we get here? Okay. Okay. I already see a conditional jump. Why? Why is there a conditional jump here? How did I already mess this up? Oh, and I want native. Not that it shouldn't really matter here, but huh. There would be a single branch because of the minus sign. No, I don't think that's true. Not if this can be a conditional move. But this is our this is this copy. Which feels like it can just be... Oh, this is definitely wrong. That should be temperature.len. But this feels like it could be a copy from temperature as pointer to t as mute pointer, and it should just copy tlen, and that should now be fine. Question mark. Shouldn't be anything conditional in there, maybe. Great. Okay. Well, we do a call to memcopy, which, like, okay, feels maybe excessive here, but all right. Actually, do we even need the copy still? We just did that to do the swap of the dot. But that may not be needed anymore, actually. Right? Because I think now we can, instead of doing that, we can just do tlen is still t.len. But this should now be no, because the dot, yeah, this should just not be skip. This should just be tlen minus 1. Always. But this one could be wrong, because this could now need to skip the dot. Ah, no. The first one is always easy because it's the one after the sign. The last one is always easy because it's always at the end. And so there's no conditional on it. It's only this one that is tricky. This is always just this. But T2 may not be there. So T2, if it's there, is going to be 3 from the end. But we might have to null it out because, yeah, we might need to null it out because this ends up being a dot instead. or this ends up being the same digit as T1, right? This could end up being the equal to T1, in which case we null it out. This would be hundreds. This would be 10, but something's still wrong here. This should just be this. And this divide by 10 here is also a problem. Yeah, something's still not right. This is always times 10. This is never times anything. And the question here is, what is this multiplied by? And this is multiplied by 100 or by 10. And if that's 10, then this will be 0. So, because this is the same check. So if mul is 10, then this should just go away. We'll still do it, but we'll multiply it by nothing. Yeah. Although this might mean that we're just doing like unnecessary multiplies, which might itself come back to be expensive. Yeah, this probably should have tests, I agree. Okay, what do we got here? Parse temperature. Sine. I mean, there's a jump right there on the sine. See, this is the thing. I don't think this needs to branch. I think there's a way to just, instead of using sine num here, to just say, like, shouldn't it be possible here to... Like, what happens here if we and with this? Right? Then we should only be keeping the sine bit, which means all the positive numbers become 0. And all the positive numbers become 0. And all the negative numbers, which we know is only dash, becomes -1. But we can't use that to multiply because we need it to be -1 and 1. I agree. This okay. I think we need some tests for this one. Test. Parse temper pt. I don't want to write anymore. Assert equal. So if I pass in 0.0, I expect it to become 0. If I pass in if I pass in 9.2, I expect it to be 92. If I pass in -9.2, I expect it to be -92. If I input 99.2, 98.2. It should be 9982. Minus 98.2 should be minus 982. And I think that covers it. Eh? Can't compare. Oh. Parse temperature. Thanks. Yeah. It's getting late. Okay, it's unhappy at 231 because this returns 736. Okay. Sign. That sign is set to 8. Oh, I'm using, okay, yeah, this is incorrect. One, two, three. Oh, 1, 2, 3, 4. 1, 2, 3, 4. I need to be less stupid about this. What? Yeah, that's kind of what I'm after. That's literally what I'm asking for. I mean, like, okay. No. Wait, am I being real stupid? Like b of minus 1? All ones. Ah, right. It counts. Yeah, okay. Okay. Someone checked this. Oh, not equal is nice. Because that becomes binary. That becomes a bool straight away. Times 2 minus 1. So this becomes a 1 if they're not equal. Times 2. Still a 1. Minus 1 is 0. If they're not equal, which means it's positive. So no, the problem is it becomes 0. And I would need it to become... Yeah, sorry, this has to be dash. If it's not equal to dash... If it's not equal to dash, that means it's a number. So we want it to be a positive sign. We want it to be positive 1 because we're going to multiply. So this is going to be true. We're going to multiply it by 2. So that's going to be 2 minus 1 is 1. Okay, great. My brain is just broken. If it is equal to dash, then it becomes 0 because it's not equal. Times 2 is still 0. Minus 1 is minus 1. So the sign becomes minus 1. Great. Yes. Okay, cool. And that's why it passes all the tests. And so now if we run this, what do we get? What do we have in here? So it still claims this is a test. But where does it jump to? It jumps to LBB 10.4. Panicking bounce check. Oh. What? Why does it... Pretty sure we already... Why? I can assert here that T length is greater than 3. How do we feel about that? That seems much more promising. Yeah, now the bounce checks went away. Greater than 3? No. Greater than or equal to 3. Yep. So now it's just that assert, which will never fire. Great. So we have a conditional move, XOR, conditional move, move, conditional move, move, compare with set E, XOR, conditional move, compare. Yeah. Take that, no branches. Watch, this makes no difference. It could genuinely make 0 difference, but we are calling it on every line. I guess compared to the hashing, it's like... Yeah, I know, we could assert unchecked, but yeah, it wouldn't make any difference because all our time is in hashing, but I am still happy. Yeah, because parse temperature was like 1% of the execution time. So it really should, if it had mattered, I would have been surprised. But it does make me happier that it's branchless. Yeah, like, okay, 2159. Is the hashing maybe doing overflow checking as well? Is the hashing doing overflow checking? I mean, it could be. It could be. Oh. That's interesting. This looks much tidier now. Unclear why, but... Okay, we're spending... 25% of our time in hashing. 50% of our time in hash map, like, searching. I'm surprised to see probe seek here. That feels weird. But okay, we're ignoring hashing for right now. Fine. Why is next new line? Huh. I'm surprised this even shows up. But it is funny though, like nothing else shows up now. It's all hash map and next new line. But I suspect the inlining is like messing a little bit with this. Actually, you know what would be really interesting here is branchless parse temp is to run this with ugh. Pull out cache grind to see what it gives us. Oh. Thanks, Valgrind. Or is it Valgrind? I think it's Valgrind. But yeah, seems like it doesn't like us using fancy instructions. Oh, we're still not inlining parse temperature. Good call. Don't think it's going to make a difference either, but... I mean, it's faster. It is getting faster. And I'm still happy about that being being branchless. I do wonder, like, if I look at this, does a load or a load select a mask up to... I see, so it does a mask up to slice length. So it's only selecting the things from there that are in the length we're looking for, which will most of the time be all of them. Because the... Ooh, what does mask up to do if that length is very long? Huh. Because most of the time, that select is just going to be with a mask of all ones. It'll only be at the very end that it's not. I wonder. Like, what? Is there a load? So const all. It's going to be of some type, I don't know yet. U8x64. No, I need to... What do they use to construct this slice? Mask splat. Mask splat of true. That's not const? What? Why? Why is this not const? All right, fine. Fine. If you're going to be like that, oh no, that only takes const functions. Fine. Fine. I just want to see if it makes a difference is all. Right. Thread local static all. That's fine. I don't care. Once, fine. It'll be a once sync. I just want to see if it works. Yeah, and then this, select slice with mask. What else do you want? Or default. Seems fine. Unsafe. Yes. It's unsafe. I understand. It's my fault if it breaks. What? Sorry, I mean once lock. This is an indication that I'm getting tired. Yeah, that's fine too. Is it copy? 64. Go away. All I want to see here is if not against is if rest.len is greater or equal to 64. Otherwise this. But actually, otherwise this. Right? Is next new line suffering from unaligned reads? Could very well be. Certainly when we're trying to use SIMD here. In fact, there's a really interesting question, right? Of like, what if we aligned the pointer to the previous alignment and then searched for the new line? We might have to go pretty far back, so far back that the U64 doesn't get us there, and then we need to 2SIMD, so maybe it's not worth it. I couldn't tell you if that made a difference. Right? Like, okay, it's dash cargo build. Time this and take it to before.text. It didn't it didn't write any of that to the file. Before.text. My computer is going brrr, but not very much because it's just a single core. Okay. And then git stash pop cargo B. So what we're trying to beat is 22.14. I mean, you tell me, right? 2156, 2214, 1577, 1588. These views seem like not really any difference. 1591. The number is lower some of the time. But my guess is also that like creating this is like not really something that matters. Right? Like, did we actually see it show up? I guess we did. Nope. But like, okay, it's load select pointer that's showing up, right? And like if I now do this and then perf record, then run that for a bit. Yeah, I mean, I agree. Less code is better if they're the same speed. It is true that like creating that mask feels like it shouldn't matter. Whoa. Why does it feel like it finished faster when I was running another perf? That seems just incorrect. What happened? Where did all my debug symbols go? What? Okay. What's happening? Why? I don't understand. But I didn't change anything. Maybe it's because we set it to be inlined? Perf is tired. Yeah, I know, right? I mean, okay, are these different? No, those are the same. Okay, great. I'm like scared to open this now. Where did all the debug symbols go? I guess now we don't even see parse new line stick out anymore because it's inlined. My hope here was that we could avoid the or. Actually, because this shouldn't even need to be this. This should be like a 64. Is there really not a just like load pointer, like without the select? Like, can I just unconditionally U8x64? Can I just unconditionally create one? There's from array, which uses self load. Yes, so there is a load. I'm being lied to. I want load. I don't understand. From array. Oh, from array. There's a const from array, and it calls load, which is not pub. Okay, I understand. Okay, so then what I should be able to do is if let okay rest u8x64 is equal to u864 try from rest. Then u8x64 from array, just from, no, not from slice, rest okay. Now I don't need the all anymore. And like, I don't think I should hit this until the end of the run. So just to see that okay. False. Why? Panic. Rest.len. Why can't I create that from a slice? Uh, all right, this spammer has to get out of here. Report. Spam. Goodbye. Um, I think you're right. The trifum requires that it be the exact same size. But surely there's a... Has array? All right, what happens inside of this? Well, that's a way to do it. So we could just cast it to an array, I guess. I just feel like that shouldn't be necessary. Like, okay, we can do if rest.len is greater than or equal to 64, then is rest.s pointer. Is there a cast array? Yeah, there is. Pointer cast array. Cast pointer cast array. Isn't that what it's saying? Right, I don't need a bunch of these anymore. I don't need this, don't need this, and don't need this. Cast away. Oh, split at first chunk. Some is rest dot split. Split first chunk. Yeah. Okay, fine. That's better. I agree. This too, I'd be surprised if it was fast. Whoa! I think it just went brrr. That's what I think. Yeah, I'm pretty sure it just said brrr. Let's see if it says brrr again. Watch it now, like 25. Okay, now it's 21, but it brrred for a second, for sure. Now it's way slower. Okay. it's just, I think it's just confused. But we can go ahead and do, where's my assembly thingy majig here? Instead of parse temperature, we could do next new line. See what we get out of that. Let's just, inline, please. Now can you give it to me? Oh, never. Sorry, that's what I meant. All right, what do we got in here? Oh, there's a lot of panic things we can get rid of here. Yeah, okay. This can go away. That's for sure. Don't need that here. Thank you. Nope. That's not what I was trying to do. I was trying to do this. Great. And then (10.1). What does 10.1 do? What? Six, 10.1. Oh, I see. Okay, this is like whether it does SIMD or not. It seems fine because this should be predictable. This is just whether we've gone halfway through what's left. Interesting. I wonder... Yeah, okay, so this does a... This feels like we could optimize, right? Like, I agree this is nicer, but at the same time, I think I want this to just be... If... I guess I'm just hoisting the bounds check, really, by doing this, right? But the difference is... So I'm just trying to figure out... This is looking at mid less than length, which the branch predictor should be very good at because we're basically always taking this branch. Okay, so this branch is probably fine. That's funny. This basically becomes a Norwegian word. Kortest, which means shortest. That's not what that instruction does, but you know. If let sum is first set, that's this one, which is a likely branch. So that's fine. The branch predictor should be good at that one too. And then there's the else branches, which is like the mem character and stuff. What jumps to 9 and 10? Oh, that's this and the slice fail up here. So this is can also be a get unchecked because there's no way it would otherwise fail. That looks a whole lot nicer. Okay. So this is now, right, and we can go back to letting this be inlined. This is now, All right. I think it's time for multi-threading. Is what I think. After, before, cache grind, heap, inline, perf data, and VG core. Let's get rid of these. Okay, let's now first and foremost do cargo B release. And then we're gonna run time dev null. And we're gonna do for n in. We're just gonna do while true. I just wanted to gather a couple of things. I think we're looking, yeah, okay, so 18. So sometimes we do really well here with the current version. Why this is sometimes 18 is still very confusing to me. 20. It's so variable even with a single core. It's still surprising to me. All right. Okay, it's just getting slower if I keep running it, so I'm not going to run it anymore. Linux mount RAM disk. I just want to see if that actually makes a difference here. What's the... yeah, okay. Actually, how big is this actually? Okay. How's my RAM? I mean, it's a little painful, but I guess 15G. Make their temp RAM disk. Temp RAM disk. Sage top say? Yeah, that's fine. Copy measurements to temp. No, to temp RAM disk. RM measurements, ln-s temp random measurements here. Just to see, you know? There we go. Now we're using memory. So it's down from 18 to 15. Yeah, doesn't make a huge difference, which I'm not terribly surprised by. I have a pretty decent disk. So I'm going to move temp RAM disk measurements back to here. No, I ran it twice. System is lower, that's true. In fact, it's mostly the system that's gone away. Sudo umount temp RAM disk armdir temp RAM disk. Cool. Multi-threading. Okay. Still has to be in one file, huh? All right, fine. Here's what we actually kind of wrote the multi-threading. We just skipped past it. The trick here is going to be that this is basically a single threaded. So we're going to go here, and then we're going to say one, which take a map of U8s and returns one of these guys. One of these guys. And it's going to here return stats. Then we're going to go back up here. Just to show, if I run of map here, stats is equal to this, then everything should be just the same. All of this is premature optimization. Yeah, I'm not even going to bother waiting for it. Okay, so now we have all of the stuff that needs to happen in one thread. Now the question becomes, how do we start multiple threads? Well, what we want to do is we want to figure out how many ways we're going to shard the computation. Like how many chunks do we want? And realistically here, the goal is probably something like the number of cores on the machine, which there is a way to do, which is the thread. They added this, right? Like CPU count. They definitely added this. Nope, I can't even do this. Didn't they add? Was it threads? Oh, they called it something. Available parallelism. That's the one I'm after. Yeah. Okay. Great. So we're gonna say let threads is stood thread available parallelism. Now this returns an estimate of the default amount of parallelism a program should use. Perfect. Unwrap. So this is the number of threads we want. And now we want to split the map into that many parts. Okay, easy enough. We take our map and we say let submaps is 0 to n threads. I don't want to do this. I think the way I want to do this is slightly different, which is let mute at is 0. Then I want to do let mute submaps is a vec. We can optimize this slightly later, but it might not be necessary. Let chunk size is map.len divided by n threads. And then I want to do for in 0 to n threads. And for each one, I'm going to, I might not even need the submaps. I can just spawn the threads eagerly. So this thread is going to start at, it's going to end at plus chunk size with a min with map.len. But we have to adjust this slightly because we want every thread to end at a new line boundary. Luckily, we have a function for that. Next, new line. So if I give this a map that starts at end, and is currently at 0, then please, oh please, where is the next new line? And the next new line is what is actually going to be our end. Plus 1. Is that broken? broken at the end of the file? Might be broken at the end of the file. Let's find out. And so the actual map that this is going to be operating on is a map from that start to end. And now at is going to be end. Yeah, at is going to be equal to end. That's where the next thread is going to start. Now, then we'll do std thread. So this is actually just going to be let mute threads is vec new. I think I want to do this slightly differently. This is going to be because the threads might finish slightly out of time with each other, and I want to start incorporating the results when the first one finishes. So we're going to do a MPSC channel. It's going to be a sync channel with a bound of n threads. TXRX. Non-zero, that's fine. Thank you. That's also fine, thank you. Consider borrowing, I will consider it, yes. Now we're going to do a thread spawn. Move in here. And inside of here, we're now going to do... Actually, I think I want to do all of this inside a thread scope. Because this gives me back a... Yeah, and then in this scope is where I want to spawn threads. The reason I want to do this is because this mmap, we've tied the lifetime to the file, which isn't technically correct. Technically it's static, but feels more appropriate to do this. So we will do this, and in here we will do scope spawn. Inside of here, we will run one map. And we will do tx.send one of map. Tx is tx.clone. And it's unhappy about me sending my mute u8. What mute u8? Ah, that's fine. Unsafe impl send for Sturvik. There's nothing scary about Sturvik as far as threading is concerned. So that's going to send the result of running 1 over map. We're going to do that for all of the threads. Excellent. Now, what's the rule here for scope? Let mute. That's going to go out here. Mute stats. Everything is called stats now. New. And here we're now going to do for one stat in RX. We're going to drop our last TX here so that this gets closed correctly. All right. Chat is upset with me. Safety. This is fine. No, I'm joking. Effectively just a vector, which is fine to send is fine across thread boundaries. And in here, what we're going to do is this, basically. So we're going to say, for, how do I want to do that? I think I might allocate strings here, actually. For kv in one stat, because the one stat here is going to be dropped at the end of this loop, which means the keys, which we were previously just re-borrowing, we're now going to want to own, but I think that's fine. I don't think this is where our timing is going to go. For kv in there, stats entry, this now is going to be unsafe. This will now become string from that. So entry of this. No. Entry of K. We can just keep the ownership of K here. And then match on that. And this, we can do this. None.insert v. This is the tricky one where here we actually need to do some dot. Oh. No, this actually does need to take it into a string, because in this B tree map, we are supposed to... I don't think it matters. In this B tree map, we are supposed to keep things in Unicode sorted order. So we do actually need this to be like so. This goes like this. This becomes to vec. I guess this can implement into vec actually, if we really wanted to make it do that. But I don't think I care. Because like technically it might already have an allocation we could reuse, but I don't care for now. So with the sum here, we're going to have to say that sum dot get mute stat dot 0 is stat dot 0 dot min, right? I should really make these actual struct fields, I know. Min of v dot 0, 1 we plus equal 1, 2 we plus equals 2, and 3 I'm sorry chat, I know, maybe we'll make it a type one day. Great. This is the readme promised. And I think I can just do into mute here, actually. So we're just accumulating the things we get out of every thread into one that is in the main thread. This is going to move the TX, which is fine. And we should be good to go. See, multi-threading, easy. Oh, well, it crashed really fast. Slice index starts at 12, but ends at 7. Great. Yeah, I figured this was probably broken. Okay. Let's do slight debugging here. So this is supposed to be start to end. Well, that sure looks wrong. Okay. What is our chunk size? What did I fuck up? I did something wrong. Maybe that is our chunk size? It's not a completely unreasonable chunk size, right? Maybe I should ask, what's the number of threads here? $32. Seems fine to me. Okay. Okay. So we find the next new line starting at end. So where is that new line? And yeah, here I could probably GDB it pretty easily, but yes, that looks incorrect. That is incorrect because this has to be end plus new line at. Thank you very much. Address boundary error. That's different. These also don't overlap correctly. So something's still wrong. What do we have up here? 37 to 1144. Yes, because we're not adjusting. There's definitely something we're not doing right here. Oh, I'm printing before I'm updating end. You're right. So here. And then what I actually want to do is I want to also print out, just to see that this isn't like completely silly, I want a map from start to start plus 10. And I also want a map from end minus 10 to end. Yeah. Stir from UTF-8. I know. Unwrap. Well, that looks correct. All of these look like the start of a place. They all have a initially starting capital letter. And the ends all end with a new line. So that also looks right. So that means this starts at the boundary of a starting station name and ends including a new line, which is what we wanted. And then at gets sent to end. So that all seems reasonable, is the thing I'm worried about. Well, we executed very quickly. We just also hit a seg. Okay, fine. Let's do... Nope. Well, that's fun. In memcar. In next new line at 236. Okay. From 147. Oh, okay. Yeah. So we just failed to find. Yeah. Okay. This is the thing I thought was going to cause us problems, right? So the problem here is we set at to the end of the previous chunk. But if that end is if that end is the end of the file, that shouldn't matter. We should stop iterating early enough that that doesn't come to... No, that's not what I wanted. Brrr. Okay. I want my debugging info back. Yeah, and then here, I need the total map length. So the total map length here is 1379, ends with 06. 79. Yeah, so we're on the last iteration. We're about to give out the last chunk, and this end ends up being equal to map length. And then we search for next new line starting there. But next new line is written so that it can't handle hitting the end of the file. We would get this, it would be empty. We would have this branch. I don't know why my syntax highlighting is now messed up. We'd have, so this wouldn't find a new line. We'd go into here, and this says we know there must be a new line, and so therefore this must be non-empty. So we skip 64, and that doesn't work because this is intended to be called only when you know that there is a next new line, which normally we know, but here we don't. If end not equal to map.len, end is if end is equal to map.len, then map.len, else this. And that way we're branching outside of this thing. This thing is called on a critical path. This is not, so we move the branch outside of there instead. And then I think this should be good. Okay, away with the prints. Away with the prints. All right, 1.08, 1.07. So that's pretty good, I suppose. Now it's parallel. It's parallel now. Okay, the Java one was 800 milliseconds, right? So now the question is, where's the time going? And perf record this. You tell me, perf. What did you see? No! No! Okay, great. Okay. 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 I see a little bit of drift here. 2% on parse temperature. What do we need here? So we're at 1 second, so 10% would be 100 millis. So we need to recover at least 10% to beat Java. Although we do know the Java ones are cheating now, so you know. I mean, it comes down to the hashing again. Oh, someone says they think we're summing the things for averages wrong. Let's, I mean, that's an easy thing to fix or to check. Output.text. And then let's just run one of the Java ones. Correct.text. I tried to write text. I swear, chat. Okay, so if I diff output.text with other correct.text. Well, those are different, but how are they different? No new line at the end of file. How about now? Okay, they're different. How are they different? What's the... Can I diff by word with regular diff? How about I just do that? Oh, yeah. 8.6, 8.5. Why does it end up being wrong? Oh, right. What are the rules? Rounding of output values must be done using the semantics of IEEE 754 rounding direction, round towards positive. Round towards positive. Positive. Round. F64 round. Round. Yeah, okay. What's the... Isn't there a round towards positive in Rust 2? This is an issue in my code? Where? When we accumulate... The accumulation down here shouldn't be the problem, because here we're just adding numbers. And same thing here, we're just adding them. We're keeping them in the max. I actually wonder whether for min, what does min turn into? I almost wonder if this could be like only overwrite if smaller. I wonder if that would make a difference. But okay. But here is where we take the sum. We divide by 10 to get back our fractional. Doing stat instead of V for the averages. Oh. Ah, yeah, you're totally right. Good call. Let's try that again. Output. No problem. No problem. Good job, chat. Pat yourselves on the head. Great. Oopsie. You saved me. It's true. Right. But the... Yeah, we're still trapped in the hash map conundrum here. Although, okay, let's try slightly more sampling here. How much data are you writing? It lost 70% of its samples. Why? I guess it's recording a bunch of data, huh? Okay. This. Oh, Lord. Be brr 1. That is indeed the one we care about. Yeah, like, okay. The execution time spent in 1 here is 99.5% of total execution, total samples, sorry, not necessarily execution time. It is true that, like, that does mean that there is some amount of time that is in our printing, but relatively speaking, nothing. And these are all essentially nothing. One of the Java implementations we looked at is using perfect hashing. It assumes no collisions. The other one handles collisions. So that one's not cheating. And we are using the same hash functions they're using, but we're not using the same hash implementation. And so they could easily end up with all the values being in distinct buckets. Whereas hash brown is not, because it's doing other things with the hashes, right? And I mean, we are spending 40% of our time in rotate right. What if we... I didn't try inverting the bits of the hash to make the high bits more impactful, because the rotating kind of does the same thing. Like, where the mixing here achieves a similar thing. Unsafe. Oh, there... Oh, that's interesting. That's something else. What if we do this instead of a rotate? And I assume these are equivalent, right? There's... Oh, actually, my printing is really slow. Now that I think about it, my printing down here is like printing small bits at a time, but it shouldn't be enough that it's like the slow part. But all right, let's stood out is stood io stood out. Let stood out is stood out dot lock. Let writer is stood io buff writer new of stood out f printf writer. It's not f printf. It's writer mute writer dot write. No, that's okay. Ignore me. Write is what I'm after. And I want to use from to write. What? Oh, I also need to use IO write, I think. Write writer unwrap. Shouldn't make a difference to this, but oops. But you'll see it was still like quite a lot slower now that this hash mixing is less good. What is the Java triple bit shift? Is that rotate right? No, it just shifts with the sign bit. So, and they were doing triple shifts here. Performs a right funnel shift, concatenates self and the right hand side with self. That could also be something useful here. But like what's the equivalent of the triple shift in Rust? I think it is the double shift. Like what I'm confused by is that the hashing here, the Java hashing hashes this way. So this is a bit preserving, sign preserving shift, but it's not a rotate. Now, we had this be a rotate, but a rotate is slower because the bits on the right need to make it to the left. But seemingly, it's also making the hash function less good. These are also U64s, so it shouldn't matter. Oh, for them, though, it's not. For them, this is an I64. It's a long. We don't actually use this value for anything, but 0. But I don't think that should matter either. Right? So why is that sufficient for them, but not sufficient for us? And that feels to me like it's probably related to hash brown's assumption that it gets the high bits. So what if we took this whole thing and rotate by right 32. So that's still one fewer rotate that we used to have. 342. Okay, so that's slower. What's interesting though is like we have this funnel shift right. I wonder if we could use this. Concatenates self and right hand side with self making up the most significant half, then shifts the combined value right by n, and least significant half is extracted to produce the result. Feels very hashy. But okay, so rotate right is what we were using when we got pretty good, like we got better performance out of this, presumably because it's mixing the bits better, right? Like this, I think gave us 1 point, what was it, 1.2? Oh, what? I think I want off this ride. Why? That is what we had, right? Yeah, that's what we had. Why is this slower again now? It got slower and I fixed the accumulator? Maybe? But that seems insane. That shouldn't even matter. That's at the end. Right? Like, if I make this now be stat again, there's no way that makes it take 2 seconds less time. There's no way. Okay, good. Good. That would be wild. I do, however, want to do this, I think. Where this is going to be print. And I want it as inline never, just so it shows up in our profiles. Moving the file into RAM doesn't make the difference here. So but like, I don't think it's the printing is the thing. And what's this? This 2% here is just leftovers. Okay. Slightly less silly print. Okay, just I wanna do this sanity check with a hash again. So if we now go back to here, and we say a hash of this, and we say a hash of this, and we a hash this capacity with 1,000. What? Okay. Don't know why that was needed. It could be that my computer's just getting sad. But look, like when we switch to a hash, we do see that these are taking up more time now and hashing is taking up less. They're using like AES hashing and such. So there's definitely like performance on the table there. Actually, that makes me wonder if go away again. If we go back to our old implementation here. And I mean, we can do that with the copy instead, right? So remainder dot as pointer, last as mute pointer, and remainder dot len. Yeah, the systime is very high. 341, 344. So that's about the same we got with ahash, actually. And and the same we got previously. So makes no meaningful difference. With our hasher, with our SIMD hasher, how does this break down now? Yeah, I mean, it's definitely worse. It's definitely worse because of the hash function. Because like with ahash, this was like these were almost up to 10%, right? I'm curious. Okay, let's go ahead and do, nope. Okay, go away. I want to just get this. I just want to see if we now do here, don't care about that. And fx hasher implements hash. We know that this is the one that gets called. Okay, hash is going to hold a U size in their setup. Write is just a write of self.hash and bytes. Okay, where's their write function? This guy, which is calls write 64. So we want write 64. We want this thing. This can go away. And so this now becomes final. This goes away again. Self.0 is write 64 of self.0 and the value, right? That's all it had. Right. Yeah, and bytes. And then what's their finish? Their finish is just self.0 as u64. And then they use hash word. And hash word is just, they're just hashing word here u64s. So this just takes a u64 and a u64. Wrapping mul, and what's the thing they use for u64? Seed 64. Okay. Okay, and what do they use for this reading? Oh, they use the byte order crate. Oh man, that's pretty annoying to bring in here. But this is just from I think this is actually pretty straightforward. It just reads a certain number of bytes at a time. So if you look at lib native Indian don't want the tests. I want the implementation, which is up here, and I want its read u64. Yeah, which is just this. From, and this is native Indian bytes to this, to this, to this. Pretty sure that's all it turns into. And then this is like an impl on u64, which we can pretty easily just say, we're just going to do this, and it's mute self 0. Nope, it is mute hash. Mute hash. Now u32 from any bytes of this. Okay, and this is this is the same except at u16. This should also be 4. This should be 2. This is u16. And this is hash word mute hash. Okay, so now we're messed up somewhere. Where did I mess up? Expected u64 found u size. Because I'm not under. That's fine. I'm just gonna make this hasher be u64. It's because I wasn't using. I'm not using target pointer width here, and so Rust isn't willing to assume that u size is u64. Now what do we get? Got worse. We were at 344, and now it's worse. Why did it get worse? The user time improved. Yeah. The broken stack trace is also surprising. We are now spending much less time in hashing, actually. It's true. Or rather, we're spending more time in these, which is promising. Interesting. Okay. Let's just to see. Okay, so now it's around 1.20. Yeah, it's just because it doesn't have to load it into memory, but like the actual performance of the system hasn't changed, right? But it should make it easier for us to compare if I stash this. Actually, here's what I'm going to do. Home dev stream. No. Copy. What I want to do is copy cargo target release brr to brr self hash. Yeah, I'm about to use Hyperfine right now. Slash pop. I'll build this. I want to copy that to fx hash. And then I want to do hyperfine of self and fx hash. What? Oh, dot slash. Yeah, so our, our hash is faster than FX hash. I mean, I do prefer our hashing function. Okay. Okay. So the other thing I then want to see is what if we do this and this. And then we call that SIMD hash. I'm hoping the stream doesn't lag as a result of me loading my CPU now. All right, self hash it is. SIMD hash. I don't like it. But okay. Commit to hash. What's also frustrating here is that this, like with this hashing function, this is the part I find hard to understand. With this hashing function, what's happening? %100% CPU somewhere. Doing what? What is it doing? What is taking 100% CPU? Okay. What is it doing? I think my CPU is tired. No, it could also be that because of the RAM disk, the computer has less space for an actual file caching, including perf.data. And so it gets sad, maybe. But yeah, what surprises me is now, like, more time is spent in hashing. But we're still faster overall. That's the part I don't understand, because the only thing we changed was hashing. So if the hashing takes more time, then why is the overall program faster? Remember, like when we were running with FX hash, for example, we could see these be like 5% and stuff. Why are they not that now? Even if it was fewer collisions, like this is the overall time spent in. Oh, it's the time spent in. Yeah, it's the time spent in get mute. Although this is now only 87%, which is kind of interesting. Where are my other percent? Where are my other percent? Where are my other percent indeed? In fact, where's my main? Perf is eating my time. Yeah, I mean, it's been a while since we ran perf stats. We can see what it says. Yeah, we do have quite a lot of branch misses now, which is disappointing. We're also taking a whole lot of branches, but it's hard to say how many of those are through the code that runs in hash brown. And we're also doing fewer instructions per cycle than we were in the beginning. Yeah, let's do perf report -- event CPU branch misses. What? Why is it unhappy with me? Where's my -e? No, that's for perf record. Yeah, it's just branch misses. But is this showing me? Yeah, this is showing me percentage of branch misses, right? It is pretty interesting that. Really? Is one. Okay, this should not be inlined. Now, what I want to do is annotate this. But I want to annotate it with nope. With showing I want to know. Isn't there now I'm misremembering my my perf report keyboard things, because there's a way to just show the source and not show the assembly. But maybe that's not in this view. Maybe L? No. L? No. Only available for source code lines. No, S all shows the source code, but it also shows inline source, which I guess is fine, and shows the assembly. But I'm looking for just the top level source of this, which I know there's a view for, but can't find it now. This is also not in. Oh, because it's inlined all of the stuff. Okay. What I wanted to find was. Yeah, I mean, that's the... But this also doesn't make sense, because if this is branch misses, clearly 36% of branch misses are not there. Right? Like, these aren't branches, so why? No, I mean, switching between local and global here is basically nothing, because all the time is spent in one. It could be where it realizes the miss, but like, where's the branch miss prediction from? Right, because what would be really useful is source annotation at this level and not below. But I guess all of these things get inlined, right? So, in particular, get mute gets inlined. Okay, what if we do this? What if we say update stats, which gets a station, which is a U8, and a temperature, which is an I16, and it gets a stats, which is a mutable reference to this. And then we take this stuff, we move it in here, and then we here do update stats of this. And then we here say inline never. And then I want to do that on this, and I want to do that on this, and I want to do that on this. T. And then now I don't even want that yet. 1. Okay, finally now we at least see what that the self time is going somewhere. Although why 3% is going to seemingly itself is a little unclear. Right, but so this 3% of the time is spent in 1, but not in any of these functions, which itself is a little odd. Right? Like, where is that time going? Like, this is now of cycles again. Like, why? Moving out of split semi. So this is the... Actually, that makes some amount of sense, right? So this is... sometimes we read into the next page, and so it needs to... The OS needs to feed us the next page, and then we're just like stuck in the read out of one of these pointers for a while. So that's not entirely unreasonable. Like, that could be what this means. Why is there a checked sub here? Well, this can certainly be get unchecked. But I doubt that it makes a difference. Yeah, that didn't make any difference. Although it did get rid of some of the noise in between. Check sub goes away. Yeah, so call split semi, and then the move out of here. Although it's interesting that that doesn't happen to next new line, because next new line should have the same problem, right? We look for a new line, and in the process of looking for a new line, we might have to traverse a page boundary and therefore wait. Right, so why is the move here the slow part? That's interesting. Huh. Okay, and then we parse temperature. So some amount of time goes to there. That's fine. But you'll see even... switch this to global. Oh. Ah, this is 50% of the time. This is local periods. It's 50% of the time that is spent in one that's not spent in children. Is this move. I see. But if we look overall, then basically none of this is costly overall. This is sometimes. This is 2% of execution time, though. So moving out of 58 out of RSI. Yeah, I mean, it is just moving the results back. It's just wild to me that it's 2% of execution time. Because station here is a slice and temperature is a slice. So like, okay, this is pointer and length of two things. Why is it anything? I'm just trying to see if there's anything to optimize here, but I don't think so. Best I could think about is like, okay, if they get inlined, then we don't have to carry 4 return values. Pointer plus length, pointer plus length. So yeah, 4 return values out of here. So that could be just inline makes it go away. Okay. Great. And if we go into the nested calls it makes, we get about 2% for next new line and 1.44 from split semi. I mean, this is just a single. Oops. Where does the time locally go here? Why do we even have a branch at the start of split semi? Oh, that's this. But that branch should basically never be taken. This is where it would be really useful to see the branch mispredictions, because this is a branch, but we should never take it. I suppose we could here do stood hint cold path. Cold path. Just a hint to the compiler. And in fact, what just as a sanity check, right? We're never taking this branch. Good. Okay. So we should hint to the compiler that this is a cold path, just so that we've done it. It's unlikely to matter. Okay. So, and I guess we could do the same for next new line up here, right? Like, this is a cold path, and this is a cold path. We don't actually want to assert that the line is less than 64 because theoretically, according to the input format, it could be longer. But I'm curious now on split semi, like what do we end up with? Yeah, so this is local period now. And so this is the SIMD. Oh, why is there a comparison at the end in split semi? That is because this should not be that. This should be, what if we make this semi-at and have it return a usize, which is where it is. And then this will be index of delimiter, and this will be that's fine. And then up here, this will be semi-at, and then we will do, that station is line get and we can also assert that semi is less than line. Line.len. And then we can say station is line until semi, and temperature is line semi plus 1 dot dot. And we know that this is true. Can we trust the perf numbers? I mean, unclear. Perf is like, if it's using hardware counters, it's usually pretty reliable. Well, we have definitely done something, because now this is down from 3% to 1%. In fact, semi vanished from the call. Oh, which makes sense, because we moved it up into 1. But if we now look at 1... where do we have our semi here? This is still doing an yeah, our assert isn't quite doing enough here, because the index is still doing a checked sub. So that's fine. Let's get unchecked. And this also is a unsafe line. Get unchecked. And just to see whether we've made a meaningful difference here. I think it was 144, I think. I guess we still have the binary around, right? Yeah, so this is now in. Nope, hyper, fine. In. We're slower. Oh, it's because we have inline never. So that's not terribly surprising. Let's keep going through these. Then we go back down to 1 here. Look at the annotation now. That's more like it. So we call semi-at, and then we just load. And then this is just unchecked sub, which is fine. That's the unchecked sub here is just the slicing we're doing to the length. And then this here. Yeah, this is the comparison we do to check that we're still, to check that we should continue looping, which is fine. This is a branch that should be very easy to predict. Shouldn't we use something other than the sequential mmap now that we're multi-threaded? I don't think so, because sequential just means that the kernel doesn't keep pages around after you've iterated over them. And that's kind of the behavior we want, because we've fully separated where the threads walk the mmapped file in. So it's true for each read that no one will revisit that read location again. And so I think this is actually still correct. Okay, next new line. What do we have in here? Next new line has a compare, and that's the compare that's the 64, which is fine because this should be very easy to predict. But why are there 2? Like, I see why there's 1. Oh, the other comes from inside of there. So this is the one that checks that the in our next new line. One is inside of here. Yeah. Okay, that's fine. That's the one that checks that this is less than the length of rest. Okay, and then we do the simd. Oh, and the other is the looking for first set. Which can also be false if we're not in the first 64. That should also be an unlikely branch. So that I think is also fine. Okay. So those two branches I think are okay. Cool. So now we're spending 91% of our time in hash map in the damn hashing. Okay. That's interesting though. So if I now go back and remove, in fact, I think I specifically want these to be inlined. And this can, yes, that's fine. And I want this also to be inlined. We'll keep update stats around because I do technically want to look at oh, is it a problem that I changed these? I think I do actually need to rerun this if I want the source annotation. First chunk doesn't have as complex of a check compared to split first chunk. Oh, that's interesting. Okay, so if I go, where's this? It's like here. First chunk. Oh, that's true. I don't know that that will matter a whole lot, but fair enough. Okay, let's see what we got here. Let's annotate update stats and see what we get. And I mean, a lot of this is going to be stuff that comes from hash brown, mostly because we have get mute and insert here, right? So there's a lot that's going to be going on. Okay, so this is the hashing of the key for get mute. Still unclear why that load is annoying at all. And this is the finish of the hash, right? So this is effectively hash 1. So hash 1 first calls hash and then calls finish. As we see those all happening here. And then the and, okay. This I think is this is the tag compare for the buckets, the groups of buckets inside hash brown. So this I don't think we can do very much about. And then this is our deref of inlined. This is our deref of Sturvec. Which it is true we have to do this check, but that should also be easily predictable. And in fact, let's do a cold path in here too, because that it should generally be the case that these are inlined. Okay. It's interesting because we might end up calling as ref multiple times on the same stirvec because we need to use it once to do the equality and once to do the hashing. And I think we can do better than that. There's like one interesting optimization, for example, which is the implementation of partial eq here, where we can actually do self.inlined last is equal to other.inlined last, and the reason we can do this is because either the lengths have to be the same. If the lengths aren't the same, then the strings can't be the same. Well, is that true in UTF-8? Are there ever strings that compare equal in Unicode even if their bit patterns are different? Depends on the collation, right? Yeah, because then this is not safe. If you can have Unicode strings compare equal even if they are not the same bit pattern, oh, that's true. I mean, we are just using U8s here anyway, so that would already be a problem. Although in this case, I don't think it's a problem because all the keys in this data set are presumably have the same encoding of the same characters. So we can be slightly assuming of normalization here. And in that case, the lengths have to be equal because either if they are the same length, then either they're both inlined or they're both not inlined. In either case, this value should be the same. And then here we could do there's like an optimization we could do here too, right? Which is we could also, if they are both inline, which is likely to be the case, then it's sufficient to just check that the pointer and length are the same. You don't need to do this part, but I guess doing this part is like basically, like it's not a lot cheaper to compare them separately. I'm pretty sure. So I think we will just do that. Well, I'm confused. Why is it upset with me? What? These aren't borrows. Do I have to do this? Okay. Okay, so that will, at least for string equality, I think it will often eliminate the need to do this conditional. Although this is still a conditional jump, right? So There wasn't a space after the second. That wasn't me. That was here, look. If I do this, it just Rust format will undo it for me. If I put it in there, it'll fix it for me. What else do we have down here? Yeah, and this is, and then this calls slice partial eq. That's what I was thinking, that we can probably here. In fact, we could, if we want to be real fancy, we can do this. But it probably doesn't matter. Okay. And then all of this stuff basically doesn't execute, which is also a little interesting. Like, why? Oh, it's because usually you can get away with just comparing the length, is my guess. So you don't actually need to walk the byte string, which is probably what a lot of this code is for. And in fact, no time is spent here, right? And then we get, in fact, okay, but where does the code go then? It really is like the hashing, and the hashing is only done for the key we pass in. So it's only done once. And then, yeah, and then the shift rights, the XOR, all of this is just the hashing. And that's where the time goes. It doesn't go anywhere else. Interesting. All right, well, if we now get rid of the inline never for, I do wonder whether update stats should be inline never. It's a little unclear to me. But let's see what happens now. Well, that seems better, right? And we can do warm up 3 or something. For eq, wouldn't it suffice to be or instead of and when the repr is exactly the same? No, because if we have a pointer to a string, then the comparison actually needs to dereference that pointer. Because we're not changing for the pointer is the same, right? Okay, well, it's slightly faster. Not by a whole lot, but it is faster. Even though the system time was longer, so that means it's even more faster. Okay. So we'll save this as micro. What else do we got? We had one more thing that I wanted to look at, which was, can we? Okay, here's a thought. What if this was a power of 2? Just throwing that out there. It probably is it rounds to the nearest power of 2, right? There's no way it just takes the user input. Because if it's a power of 2, then you can like do a bit shift instead of a modulo and everything is happier. Nope. Okay, then we will go with 1024. And like... I mean... Is that also faster? I think we need to stop soon. Yeah, okay, so that's not faster. Cool. Just as a sanity check, you know? Great. So power of 2. And then right, the U size. Someone pointed out that we have... Well, this U size doesn't matter too much. I don't think we want to get rid of that one. But the value we store in the map... Where's my value? Okay, this. Okay, fine. We'll make it a struct. We'll finally make it a struct. Struct stat. And it has a min, which is an I16, a max, which is an I16, a count, which is a U32. Okay, let me do these one at a time so that we change one thing at once. And it has a len, which is a... What do I currently have it be? U32? And then here... Oh no, I have an I64 and a U size. That seems excessive, right? I have a sum, which is an I64, and a len, which is a U size. That's what I currently have. Stat.sum, stat.max, stat.count. Let's keep it count. And then this is min. This is sum. This is count. This is max. Max, min. So verbose. Sum, count. This can derive, debug, clone, and copy. That's fine. Somewhere else here. Stat. This should be stat. This should be or default. And then we need to do, where's my stat? Up here. Impl default for stat. So min, sum, count, max. Then down here, this is now going to be min, max, count, sum. All right, it's a struct now. I hope you're all happy. This better not change execution time. don't think it did. Struct. Statistical outliers were detected. Oh no. Yeah, okay. I don't think this is faster. It better not be faster. Yeah, okay, great. Brr in and 3 can go away. And brr self hash can go away. And brr in is now brr in, which is just brr. Great. I'm glad we're all in agreement. So it's a struct now. And then some people were upset with me because this feels like, okay, it's 1 billion rows. So I don't think it can be an I32. Because it can be 100 billion. And it needs to be an I because they can be negative. Count, though, can be a U32 because there are at most 1 billion rows, and U32 goes to 2 billion. I know it's per city, but we don't know that all the measurements aren't for one city, right? U32. So I want Burr and Burr U32. Maybe also the sum. I don't think the sum can be an I32. I mean, I agree in theory it probably can, but I don't think we're guaranteed that that is the case for this data set. It's a max of 10,000 cities, but it could be one city is the problem. We did save 8 bytes per entry, but like, so it's slightly faster, I guess. Smaller entries. Running average is actually pretty hard. The way you do it is basically this. You keep track of the sum on the count and you compute them at the end. Now, there's one other thing that I want to see. So there was a really cool article by someone who tried this in Rust. And now, here, no. Here, no. Here. Yeah, Ragnar, or Ragnar, probably Norwegian, who did this challenge in Rust. And they've done a bunch of things, including with flame graphs. It's a really cool article. But one of the things, I was just like skimming through, and I noticed that there is purging all branches, faster perfect hashing. I mean, these numbers aren't comparable, right? Because we don't know how many cores they have and what CPU they have and everything. Oh yeah, this is the, you don't actually need to do the minus B0 because you can just do it at the end, which is fun. Two max calls can be done using SIMD is also pretty fun. But one of the things that I saw was, I can't find it now. They've pointed out that it can be faster Now I can't find it. It can be faster to not run min and max, but only do like overwrite if less than and overwrite if more than. Min. Yeah, here, branchy min max. So you make it branchy. And then these branches are almost never taken because usually you're not changing the min or max, which I thought was interesting. And notice that this has a minus and this has a plus. But like, will this make a difference? I find it hard to believe, but let's see. So this would be in, I don't think we care about it down here, but we care about it in the critical loop in 1, which is, oh, it's confusing. The 1 is below the other ones here. So it's like, if t is less than stats.min, then stats.min is t. And if t is greater than stats.max, then stats.max is equal to t. So this is now min-max. Can min or max temperatures be more than 255? No. They're guaranteed to be between minus 99.9 and plus 999. But because we're removing the point and treating them as I16s, then yes, they can be more than 255. Yeah, min-max is faster. That is pretty funny. But it's also surprising to me that this doesn't show up. I guess it's such small percentages, right? That like, that's what we're chasing now. Branchy min-max. I know I still have some inline nevers, but they're kind of on purpose, so that we get to break out both the one function and the not update stats, but the print function. Parse temperature is now being sad. And get mute as being sad. And I guess now we're looking for small wins, right? There's a whole bunch of code down here that never gets called, which is fine. Give me the source around it as well. And it's like, it's all less than 1% now here. It's like this stuff for the asref, which we need in order to call hash. Although, no, we don't. We could actually, for hash, we don't need that test, which avoids the brand. No, we do need. Yeah, we do need it because in case it's longer, it just happens to never be. What about this stuff? This jump. This is inside of hash brown, so this we don't really get to do anything about. This is the hashing, which like, if you have a better hash, call me. And then we have some like tiny 0.2 here. But this is what I mean. Like, I feel like the min max didn't really show up as something that cost us time. Oh yeah, this is the parsing. It is funny because when you look at the parsing, right, like it is true that these are small numbers, but they do kind of add up, right? So there's 0.22, 0.31, so we're at 0.5, 0.6, 0.7, 0.8, 0.9, 1.1. So this does end up being 1.1, 1.7, 1.8, 1.9, 2, 2.3. Yeah, so like there's 2.5% that goes into parse temperature, which I think actually is what it said out here. And yeah, okay, great. 2.26. So so that time does go in there. Is there anything we could do to that code? Oh yeah, here's the stat stuff. I mean, you see there's like no time that goes in here, right? And I guess that's the observation, that this jump is basically never taken. Interesting that we don't even get any samples from this because it's so rare. Which is actually a little surprising, but all right, but if we go back up to the time parsing here, like where are we spending the most amount of time? We have the XOR. As a compare. Oh, we're doing these compares a couple of times. I think we can probably simplify this because that compare is the same as that compare, which is the inverse of that compare. And then this, we could remove the subtraction for like 0.1%. Although we do it in each digit we parse. And so in theory, we could do a SIMD subtract here, but given we're talking about 3 digits, it probably doesn't make a whole lot of sense. Conditional move. And I wonder if we could avoid this multiply by 0 and instead just conditionally take the value. So, okay. Isneg is T0 equal to B dash. This is not isneg. This, I feel like the compiler should be able to hoist this, right? Isneg. And then here, what are we trying to look for here? This is like let has dd. This is also if has dd, then this, else 0. So that also feels like I'm trying to figure out if we can here do a oh, this can be an assert unchecked. What? Yeah, so these minus B zeros also feels like we could get rid of, but we would need to. Doing so is actually a little bit annoying because we're also multiplying them by 100, by 10, and by nothing. Skip is isneg as use size. Is that true? Yes, that's true. And then let's now see if I quit this and do cargo ASM. Cargo ASM parse temperature. I might have to put inline never on that. Yeah, okay. Inline never. So what do we have here now? No, now we have some jumps in here. We have a jump here. Has DD has now become a jump, which I don't really understand why. I guess, so it is more likely that it has double digit than not, so maybe the branch predictor is okay there, but this feels like it should just be a conditional move, right? And then we're also getting a jump here on the is if has DD. Yeah, that's what I was worried about. That's why we pulled this mole trick of this being if has DD, then 10 else 0 times. This is really, I guess, 1. Which I think then just becomes I16 from has DD, right? And in fact, this, and I mean, this is getting kind of stupid, but it becomes I16 from has DD times $90 plus 10. Right? So if we have DD, if we have double digits, the multiplier should be 90 plus 10. Otherwise, it should be 0 plus 10, which is 10. We could do a SIMD here. It's true. We could do a load select with a filter over the dot, but I think that got rid of the branches again. Yep. These are all now conditional moves. And just to check that it's still, okay, it still does that. And now, if we now copy this in, and this is now parse. Why is this version slower? It should not be slower. Okay, they're basically the same. But now, okay, let's go into one. Oh no, I'm losing my symbols again. We don't know why this happens. How about now? No, no, don't lose me my symbols. Oh, no, I think, okay, this time it's okay. So we were hoping that we shaved some of the time off from the parsing, but doesn't really look right like it, right? It was 2.7, no, 2. It was about 2.5 previously, so we didn't make it any faster. But a lot of it is now in this one sub. Why? That doesn't make a whole lot of sense either. Let T2. Yeah, it's probably misattributed here, but it's like, yeah, now we're down in the hashing. This is an iml here, and it doesn't even show up. Let T2 is tlen minus 4 minus skip times 10. I don't think that works because the length can be well, negative numbers would then mess that up, right? That wouldn't work. +1 to select unpredictable. Oh, stood hint select unpredictable. Okay. Predictable. There was also an interesting post by someone here who's like, they got it down to 0.145 seconds with the default dataset that accepts all valid inputs in C++. And in this post, they go through like, they have a bunch of ideas of things that they do. I haven't actually read through everything here, but like, it seems like they have some sneaky things that we should, that we could, sorry, not going to say we should, but that we could also make use of. But we're not actually going to do that. Unsigned int overflow hashing. Won't they just read them as U64s? Like just add them? Select unpredictable. Returns true value or false, depending on the value of condition. With a hint to the compiler, condition is unlikely to be correctly predicted by the CPU branch predictor. I see. I mean, sure. Select unpredictable. True and false? Sure. That is now the... Oh, no, it's that one and this one. No, true, false. Although I suppose we could do the same down here, for example, instead of this like sneaky business. Isn't parse temperature most 30 milliseconds of the runtime? Yes. It's most well, it's at most 2% of samples. But you have to remember that it's it adds to the sequential time of the program in a sense, right? Because all the threads are running in parallel. And so if each one is spending 2% of time there, then all of them will get shorter. But yes, I think this is like hyper optimizing things that matter much less. Which is it's a good prompt that maybe this is not the place to spend our time. But it's fun, you know? Okay. More. Okay. I think we need to stop here. Because I think the place we're going to get any further now, right? If we look at perf record, just to pull it up one last time. I'd love to see is simply adding up the U64s with overflow for hashing. All right. We'll try it. It's all I can give you. So that would be self.0, and then it would be bytes chunks exact, no, chunks as chunks of length 8 and then we do self for chunk in chunks self.0 plus equals chunk and then well, it sort of depends on what addition you want to do here, right? Like, should this be a U32? Should this be a U64? Because the problem you run into is that many of our strings won't even be 8, or some of our strings won't even be 8 characters, but okay, so we'll do 4, and then we'll do this, and this will be on the remainder. U64 from any bytes. Remainder remainder, I can't spell, from any bytes. Self.0.wrapping add. Self.0.wrapping add. From what do you want to do with the rest? Do it again, I guess. But no, that feels this is a remainder of 4. I think we just do 4 r in remainder self.0 plus equals r. When there be at most one 4-byte remainder chunk. Yeah, there'll be only one. At most one. And I mean, maybe we just ignore this remainder. But time. No, cargo B. Add. Watch this like halves the compute time. I don't think it will. Nope. It's slower. Alright, but let's... Alright, let's not fully give up here yet. Let's try this. Just so I don't get accused of not having tried it. That's even worse if we don't add the remainder. So that's fun to see. Okay, so what if we just do the 4 and we ignore the remainder? Right, but there was a claim that maybe this should be 2 BE bytes. 2 BE. Because the something, the high bits might matter more for hash brown's grouping of buckets. Nope. That's for sure slower. That's for sure slower. Yeah, I think, I don't think that's a winner. Okay. So what I was about to say was, if I do perf record and then perf report, and we look at the output, like if we look, no, inside of here, oh no, oh no, oh no. Okay, good. Like our time here realistically is spent in update stats, right? And update stats, basically all of that time is spent here. So can I change that? No, I can't. Okay. So what these add up to 80, 92, 93. Okay, basically all of it. So all of update stats right now, if this is to be believed, is in just the hashing. And then there's a little bit in parse temperature. It's already branchless, right? But it does have to do integer parsing. So it does have to do some like multiply by tens and whatnot. So I think the hashing is the one to get at next. And maybe that is writing our own hash map, but the moment we do that, I feel like something is off. Just because I know hash brown is so optimized here that like it just feels like something else is off. I think actually the hash function is probably the place to spend time instead. And I mean, even if you buy like 10% here, then we're already quite a lot faster. Yeah. Interesting. Anyway, okay. I think we should now actually stop because I need to eat something and drink something and go to bed. But I hope that was interesting. I hope you enjoyed follow along. I hope you learned something, even if we didn't end up faster than Java. You know, Java beat us. We have to admit when we've been beat. Although, how much code do we have? We also don't have too much code, like 300 lines. And how much code is this solution? 400 lines. Okay, so we have fewer lines and also worse performance. So, you know, I'll take it. So what I'll do is I will upload this to YouTube as usual. If you watch this on YouTube, you already know this. But I will also put a link when I upload to the Git repo of where I put brr, which will probably just be github.com/johnwho/brr. And so if you want to then take a stab at making this faster, and remember, don't break the rules, then please do. No external dependencies, no breaking of the rules. And let me know if you find a way to make this magically way faster. But in the meantime, thank you in chat for joining me. Thank you for watching. And I will see you the next time we do a stream, whatever it might be. Thanks, folks.